Just a minute, sir. It's coming.
No, sir. Sir, and the voice is very low.
Now it's coming. Your screen is visible.
Okay.
Yes, sir. Visible to also.
Yes. Okay. Okay. So without any further delay, I will directly go into the talk. So this talk will be about computational semantics. And I would first acknowledge that most of the slides in this presentation are taken from the Coursera course on natural language processing, which is offered by Jurafowski and Martin. And then I added a couple of slides and added some contents from here and there. Okay, so okay, so I will start with this NLP pyramid. So this is how the processing in NLP looks like. So at the very base of the pyramid, we do lexical analysis or morphological analysis. In fact, the lower three stages are very similar to what you do in compilers. So you do lexical analysis, then syntactic analysis, then semantic analysis, because in compiler you also deal with languages. So that is also the case for when you are dealing with natural languages. So at the very beginning, we do some lexical processing or morphological analysis. Then we do some syntactic analysis, typically like PS tagging and parsing. And then comes the semantics. So the study of semantics basically means that the study of meaning of words. And why do we care about like morphological analysis, syntactic analysis, semantic analysis? And then we have pragmatics. Pragmatics is at the very top, and it is a very difficult thing. So, I mean, morphological analysis, syntactic analysis, semantic analysis, all of them deal with the sentence level. So typically, if you have any tool for these processings, so your input will be typically a sentence, but in the pragmatics or discourse, your input will be the entire paragraph or an entire document. Okay, so pragmatics and discourse is very difficult. So, but this lecture is about semantics, and semantics comes only when we have already done the lexical analysis or the morphological analysis and syntactic analysis. Then comes the how do you resolve the ambiguity in meaning. And that is the main reason ambiguity is the main reason we study natural language processing. If languages did not have any ambiguity, then NLP would have been a very easy subject, just like a compiler, and we would have achieved very, very like high accuracies in all the processings. But that is not the case. NLP is a topic in artificial intelligence. Okay, so first I will introduce some concepts from linguistics that relate to semantics, and then I will go into the actual tasks. So first, what do you mean by word senses and the different relations between word senses? This is just to start with. So by lemma, we refer to, if two words, if they have the same stem, they belong to the same part of speech and they have roughly the same semantics, then we say that they have the same lemma or the citation form. By lemma, we typically refer to the dictionary head words. Say, for example, cat and cats, both of them have the roughly same meaning, okay? And they have the same stem, cat, and the part of speech is noun, okay? So we say that both of them have the same lemma, which is cat, which is the dictionary entry. And word form are the inflected words as it appears in the text. So if you have banks, so the corresponding lemma is bank. Or if you have the word surface word playing, the corresponding lemma is play, and so on. Okay, so here are some examples. Like the last example is a Spanish example, but this is what this is basically the difference between lemma and word forms. Now, lemmas have multiple senses. That is the main problem in semantics. So a lemma can have multiple meanings. Say, for example, if you look at the if you look at the two sentences, in both the sentences, you can see the word bank appearing, But if you read these two sentences, you will understand that in both the sentences, bank appears in a completely different sense. So in the first one, it appears in the context of like financial bank, whereas in the second one, it appears in the context of like a river bank or sloping land kind of a thing. Okay. So by sense, we refer to a discrete representation of an aspect of a word's meaning. By sense or word sense, we mean that. And in that respect, then the lemma bank has at least two senses. In fact, it could have many more senses. So we would say that bank one, which refers to the first sense of bank, is the financial bank. And the second sense is the sloping land kind of thing. Before this, I just forgot to open. Yeah, I will need this for the presentation anyways. Okay, so now we will go into some other terminology, and their relations with respect to meanings of words. So homonym is one such concept. So words that share a form but have unrelated or distinct meanings. So when you say words that share a form, it could either be orthographic form, that basically means the spelling spelling of the word. Is there any problem with my audio? I don't know. I checked the internet. The internet seems to be pretty fast, but I don't know what is the problem. Okay, so homonyms are words that share a form. Either it could be either orthographic form or the phonetic form, which refers to the pronunciation of the word. Say, for example, bank. We have already seen that bank has two different senses, and in both the cases, the spelling bank as well as the pronunciation of bank, they are the same. So we say that these two senses share both the orthographic form as well as the phonetic form. Okay. Similarly, if you consider a bat has two different senses. Like one belongs to the flying mammal, whereas the bat, like you could also have baseball bat or cricket bat, like a playing instrument. So two completely different senses of bat. So we would say that these two senses are also homonyms. Now, if the two senses are same with respect to their orthographic form, that is the spelling, then we would say that they are homographs. So just like that, so this bank 1 and bank 2, they are homographs. Similarly, bat 1 and bat 2, they are also homographs, okay? Because they have the same spelling. And then homophones, if two words are pronounced in the same way but has different meanings, then we'll say that they are homophones. So homograph basically means same graph or same spelling, and homophones basically refers to same phone or the same pronunciation. So then WRIT, right, and RIGHT, they both have the same pronunciation. So we will say that they are homophones, but they are not homographs. Similarly, peace and peace, they have same pronunciation, different spelling, and different meaning. Okay, so they are homophones, but not homographs. So just like this, you could also have homographs which are not homophones. In fact, we will soon see some examples, at least in English. I don't know such examples in Hindi, but I know some examples in Bengali. But at least in English, we will see some examples for this. Homographs that are not homophones. Now, why should we bother about homonyms? Because homonymy causes a lot of problems in NLP. When we have a word, for which the spelling is the same, but it has different meanings, or when we have a word that sounds the same, but it has different spellings and different meanings, then we have some problems. Okay, so say for example, we are doing information retrieval or web search, and the query is bat care. Now you will have to first resolve whether this bat is referring to the bird, or this bat is referring to the cricket bat. Like maybe someone may be interested in taking care of his cricket bat or baseball bat. Maybe he's very much into playing, so he all he needs to know is about how to take care of the bat so that it he can increase its longevity or whatever. Okay, so first you'll have to do this, resolve the meaning in the resolve the ambiguity in the meaning, and then you can do the proper search. It also causes a lot of problem in machine translation. Particularly in machine translation, it is very useful, this resolving this ambiguity. Why? Because if you think of the bat as the animal or the bird, then it has a different translation. So this is the translation of bat in Spanish, and this is the translation of bat, like the cricket bat or the baseball bat in Spanish. Similarly, if you are going from text to speech, if you think of a speech synthesizer, so this is the example. I mean, the word bus, B-A-S-S, when, I mean, it could either refer to fish. You must have heard of sea bass or bass fish, which is kind of very popular for fish fry. And you can also have bass music, okay? So like bass guitar or bass voice, so which relates to the musical concept, but it has a completely different pronunciation when you are talking about the musical concept, okay? So now, say for example, you are building a text, speech synthesizer. So you have this word. Now, unless you don't know what exact meaning we are referring to for this particular word, you cannot produce the right pronunciation. Because if we are referring to fish, then you will produce the bus sound. But if you are if you are talking about the musical concept, then we are talking about the bass. Okay, I mean the pronunciation should be bass, not bus. Polysemy, okay. First of all, same is the Latin word which basically means meaning, and poly basically refers to multiple. So when words have multiple meanings, that phenomenon is referred to as polysemy, and that particular word is said to be polysemous word, okay? So it has polysemes or multiple meanings. Now, if you look at these two sentences, which both of which contain the word bank, the bank was constructed in 1875 out of local red brick, and I withdrew some money from the bank. Now, in both these sentences, you have the word bank, but there is a slight difference in the meaning. Why? Because the sense one, it talks about the building that houses the bank, okay? Whereas the sense two, it refers to the financial institution. I mean, say for example, somebody says the bank was renovated in the last week or whatever, in the last month. So then we are referring to the building, not really about the bank, okay? So there is a subtle difference in the meaning. So a polysemous word has related meanings. I don't know, I mean, at least in the NLP course, they define polysemy like this. But in general, when a word has multiple meanings, we refer to it as a polysemous word, okay? And in fact, most of the non-rare words have multiple meanings. In fact, if you go to any standard dictionary, like a very comprehensive dictionary, I will soon see you some example with WordNet for that. And you will search for very common words, like be it any word, like any noun or verb, you will find many different meanings for those words. I mean, most of the meanings are like very rare meanings, but still, I mean, they have those, they are used in those senses. Metonymy is another relation for polysemous words. So it is a kind of systematic polysemy. So lots of types of polysemy are systematic. So say, for example, in the last slide, we saw the example of bank. So this same relation also holds true for words like school, university, or even college. I mean, so say when you say school, it could refer to the building that houses the school, or it could refer to the institute, okay? So all of these nouns, they could refer either to the institution or to the building. Similarly, so I mean, this metonymy in this case is the relationship between the building and the organization. Other such kinds of systematic polysemy also exist. Say, for example, I say I love Tagore, okay? Then it could mean that I love Tagore as the person, or I love his writings. So particularly for author or like musicians or composer, it is the case. So there is a metonymy relation. Similarly, also for tree and fruit, plums could refer to the fruits, or plums could also refer to the plum trees. Okay, so these are metonymy relations. Now, how do we know when a word has multiple senses? So there is a thing called Jugma test. So let us consider these two examples. Let us consider these two senses of serve, okay? So which flights serve breakfast, and does Lufthansa serve Philadelphia? So we have these two sentences that both of which contain the word serve. And so what we will try to do is we will try to make a sentence by combining these two sentences. So we can either say, which flights serve breakfast and Philadelphia, or we could say, does Lufthansa serve breakfast and Philadelphia. Now, none of these sentences really make any sense because these two sentences are really different. So these serve breakfast basically means that they provides breakfast, whereas this sentence serve Philadelphia basically means that they provide connection to Philadelphia. Okay, so they fly to Philadelphia. So that is why none of this conjugation may really make any sense. So when the conjugation does not make any sense, then we will say that perhaps they are used in different senses. Okay, so since this conjugation sounds weird, we'll say that these are two different senses of serve. Synonyms, you must know about, I mean, we all know about synonyms. So what that have the same meaning in some or all contexts. Say, for example, couch sofa or big, large, water and H2O, they are all synonyms. You can replace any word by its synonyms in most of the context, okay? Not in all contexts. We will soon go see why that is the case. So two lexemes, lexemes basically refers to words. Two lexemes are synonyms. If they can be substituted for each other in all situations, and if so, if that is the case, then they are said to have the same propositional meaning, okay? But there are really very few or almost no examples of perfect synonymy. By perfect synonymy, we refer to those words that can be substituted for each other in all situations, in all contexts, okay? Even if many aspects of the meanings are identical for the synonyms, they might not be replaced for each other. I mean, if you replace a word with its synonym in all the contexts, these might not preserve the acceptability based on notions of politeness or slang or register or genre, etc. So here is an example like water and H2O. Like say, for example, I mean, you know that water and H2O, they are exactly the same thing, exactly the same concept. But still, we do not mention H2O and water in the same context. So we never say we will drink water. Okay, we say, I mean, we never say we will drink H2O. We use H2O only in the context of science or maybe in the context of chemistry. So that is the point. Even though if two words refer to the exact same thing or concept, they might not be used in the exact same context because of these issues like politeness, slang, register, and so on. Here is another example. Consider the two words big and large. You might, to you, it might sound like big and large. They are exactly same. They do not have any difference whatsoever. So are they synonyms? Now let us consider these two sentences. How big is that plane? And would I be flying on a large or small plane? Now in both the cases, you can substitute the word big by large or large by big in both the sense. So you could say, how large is that plane? It still make the sense, perfect sense. You could say, would I be flying on a big or a small plane? So that also sounds perfect. I mean, no change in meaning. But let us consider this. Miss Nelson became a kind of a big sister to Benjamin. Now, if in this sentence, if you try to replace big for large, then that does not mean the same thing, okay? Because, why? Because big has a sense that means being older or senior or grown up. So that sense is missing for large. So that is why we say that big and large, they are not perfect synonyms. They are synonyms, but they are not perfect synonyms. Antonyms. Antonyms is just the opposite relation of synonyms. So senses that are opposites with respect to one feature of meaning. So again, we will look into this one feature of meaning. So otherwise, they are very similar. Say, for example, dark and light. So it is about brightness, but I mean, we use the the word dark and maybe bright, okay, in the same context, or short and long, okay. I mean, if you look at the words that appear near this short or long, they are very same, but yet they are very different in meaning, the short and long, fast and slow, and so on. So more formally, antonyms can define a binary opposition or be at opposite ends of a scale. Say, for example, long, take the example of long and short. So if you think of a scale of length, then long will be at one end and short will be in the other end. Similarly, if you think of a scale for speed, fast will be at one end of the scale and slow will be at the other end of the scale. Or they could be reversives. Reversives basically means they would point to opposite directions. Say, for example, rise, fall, or up, down. They are similar concepts, but they point to opposite directions. Now, there is another important relation, hyponymy and hypernymy. So one sense is said to be a hyponym of another sense if the first sense is more specific, denoting a subclass of the other sense. So car is a hyponym of vehicle, just like that mango is a hyponym of fruit. And the other relationship, the reverse relation or the converse relation is called said to be the hypernym. Okay, so if car is the hyponym of vehicle, then vehicle is said to be a hypernym of car. So it's like subset and superset. So the subset is referred to as the hyponym and the superset is referred to as the hypernym. Okay, similarly fruit is the hypernym of mango. So they go by different name, like you can say hyponym, hypernym. They are also referred to as a superordinate, subordinate, and you can also think of it as subset and superset. Okay. There are some relations, there are some properties of hypernymy and hyponymy relations. So the class denoted by superordinate, that basically means the broader concept of the hypernym, extensionally includes the class denoted by the hyponym or the subset. Okay. And entailment essence A is a hyponym of B if being an A entails being a B. Okay, so take the example of mango. We said that mango is a fruit. Okay, so being a mango means that being a fruit. I mean, if I say this is a mango, then this must be a fruit. Okay, so that is the entailment kind of thing. So entailment is kind of an inferencing kind of a thing. Okay. And hyponymy is usually transitive. So if A is a hyponym of B, just like in sets, A is a hyponym of B and B is a hyponym of C, then A is also a hyponym of C. And another name for this hyponymy relation is called the is-a hierarchy. So if say mango is a hyponym of fruit, then mango is a fruit. So this hyponym relation, you can think of it as a is-a relation, okay? Or you can also say that B subsumes A. I mean, if B is the hypernym of A, then it is said that B subsumes A. Now, WordNet, I will talk about WordNet. So I will give some examples. That is why I opened the WordNet application. So WordNet is a semantic ontology. It is like a machine readable dictionary, but it is much more than a dictionary. Okay, so it has both classes and instances. Now, an instance is a very specific individual or a proper noun that is unique entity. Say, for example, we will say that San Francisco is an instance of city. Okay, we will not say San Francisco is a hyponym of city. Okay, but city is a hyponym of a municipality. Typically, when you have a very specific thing like a proper noun or that kind of a thing, then we say that it is an instance of the class. Like say, for example, we will say that mango is a hyponym of fruit, but we will say that Alfonso is an instance of mango. Alfonso is not a hyponym of mango. Okay. Okay, now I think, yeah, so we need some kind of a, like a machine readable dictionary or thesaurus or kind of a semantic ontology like WordNet. Now, why do we need this kind of resources, semantic resources? They are used across all applications. In fact, if you are trying to build an NLP system that does something, if you want to do deeper NLP, then you must do some kind of semantic processing. If you remember the pyramid that I showed for the NLP pyramid, you at the top, very top, you have the semantics. I mean, before pragmatics. Okay, so I mean, if that part goes missing, then I give the example of like bad care. Similarly, you can also have many different examples. So where one of the search terms, it has multiple different meanings. Okay. So if you do not do that, then your search results will not be the same. Okay. Similarly, it is also important for information extraction if you are doing question answering or summarization. Almost every NLP applications must involve some kind of semantic processing, and for semantic processing, we need some kind of either a machine readable dictionary or thesaurus, or some kind of semantic ontology. Now, WordNet 3.0 is a hierarchically organized lexical database. So that's the difference between a say ontology and a normal dictionary. So dictionary is not structured in a hierarchical way, but in the WordNet, we will soon see that every concept is structured in a hierarchical way, in like a tree structure. Okay, so all the different concepts, they have relations between them. So it is a kind of thesaurus, but it has, it is much more than a thesaurus. It has, I mean, soon you will see that it can be used for many different applications. And these are just some statistics about WordNet 3.0, 3.0. So there are like more than 1 lakh unique noun strings, and around 12,000 verbs, and around 22,000 adjectives, and about 4,000 adverbs. And so these are about the strings. Okay, so there are 1 lakh, more than 1 lakh, like 1 lakh, almost 18,000 nouns. Now, many of these nouns belong to multiple concepts. Okay, and moreover, many of the nouns are it could be the case that you have 2 different, or maybe even 4 different words, noun words, all of which have the same meaning. Okay, so there is no relation between, I mean, you cannot really say, even if all the noun words have at least one meaning, and in majority of the cases it might have more than one meaning. So it may not be the case that the number of total noun concepts may be less than this, because one concept can consume multiple different strings. There could be many synonyms belonging to a single concept. So this is how maybe I will now go to that. Yes. So this is the GUI for WordNet 2.1. WordNet 3.0 does not have any GUI, so the raw files are available for WordNet. But this is how the WordNet looks like. So if you, I mean, in the app, the font size are very small, so I'm not sure whether you could see this, but I hope you can see this. So if you search this word bus, you will see that it lists 8 different senses in the noun category and 1 different sense in the in the adjective category. Okay. Now most of these senses, noun senses, they are actually they belong to 2 broad coarse-grained senses. So in fact, I think I have somewhere, I don't know, maybe later. So I think there are 3 senses that belong to the fish sense, and all of the rest of the senses, the 5 senses, they belong to the like the musical sense. Say for the example, the first one, the lowest part of the musical range. The second sense of bass is the lowest part of the polyphonic music. The third sense is an adult male singer with the lowest voice. Okay. The fourth one, it talks about the fish sense, the lean fish of a saltwater fish, blah blah blah. Okay. So we have these different senses listed. If you take a common word like, say for example, cricket, you know that cricket can be used either in the sense of insect or in the concept of like the cricket as a game. Okay. Now if I choose this advanced option, so you will see that every word, I mean every concept, so these are the concepts. Okay, so you will see that every concept has this like some kind of unique numeric ID at the very beginning. So this is called the synset offset, and this is the unique ID for every synset. So every synset has a unique synset offset, and this is very cleverly designed. So in fact, this is, I mean, you have 4 different files for, because I mean, OneNet is like, if I say, for example, I search with off, it does not show any meaning of off, because off is a preposition. Off is not a content word. By content word, we refer to only nouns, verbs, adjectives, and adverbs that have some senses. Okay, the rest of the categories, they are called function words, and often they're treated as stop words. So I took the example of cricket, okay, or even I can take the example of football maybe. So you can see that here are 2 different senses of football are listed. So the first sense, one sense refers to the football as the object. The other sense refers to the football as a game. Okay, so these are the 2 different senses of football. But my point is, since the WordNet provides 4 different files for basically that provides the definitions of the senses, okay, and the relations. I mean, for a particular sense, it is connected to many different other senses via some relations. Like it could be a hyponym relation, hypernym relation, metonym relation, or there are many different relations. I think I have a later slide where we talk about the relations. So in that file, So it basically says that, I mean, if you must be aware about the EPSIC and EPTEL in C. So if you just do EPSIC with this ID, with this insert offset, it will go at the beginning of this sense in that file. Okay, so that is why I'm saying they have, I mean, in that sense, then no two sim sets can have the same sim set offset, since because, I mean, with a particular file offset, you can have only one entry at that particular point. Okay. Sorry about that. So the sim set is the synonym set. I mean, sim set is basically an acronym for synonym set. The set of near synonyms in which instantiate a sense or a concept with a gloss. Okay, so we say that, say for example, take a common word like say lad. I don't know how many synonyms. Okay. So this is a concept. Okay. So this chap, fellow, feller, lad, gent, fella, all these words have the sense which refer to a boy or man. Okay. So this is the, like, if I close the advanced option. So all these words, I mean, these words are synonymous. So they form a synset or a unique concept. And that, I mean, this is the definition. Okay. So this is referred to as the synset, this set of synonymous words. And this part which defines the concept is called the gloss. Okay. And these are, I mean, the things that you see within double quotes, they are just example sentences in which you could see some of the synonymous words appearing. Okay. So this thing is the synset. This is the gloss, and these are like example sentences. Okay. If I take the same example, chump, that is shown in the slide, you will see that the chump has only one sense, which basically means that a person who is easily gullible and easy to take advantage of. And there are many synonymous words. Say, for example, chump, fool, girl, fat guy, whatever. All these words, they have this particular sense. Okay, but it is not the case that all these words. I mean, it could be the case that, say, for example, mug. If I say, I mean, you know that mug has a different sense, like a cooking utensil or whatever for holding liquid. Okay. So, in fact, if I go back to the advanced option, we'll see that it basically says that the first sense of chump, because chump has only one sense, the second sense of full, the ninth sense of mark, and so on. So mark has many different senses. Okay, and the ninth sense, you will notice that the ninth sense is referred to this particular concept. Okay, and I mean, when it shows the different meanings, it shows the concepts by the order of frequency of their appearance in a particular corpus. I think I'm not sure which corpus they used for this frequency study, but at the very beginning, you could see the frequency of these concepts, which were found in some corpus, and some of the senses were not found in the corpus. So that is why they do not have any frequency information at the beginning. Okay. Now, WordNet has this hypernym relation. So we have already discussed about the hypernym relation. So if A is a type of B, then A is the hyponym and B is the hypernym, just like A is a subset and B is the superset. Now, if I go to the, say, for example, I take the example of cricket. Okay, so the first sense refers to the insect, and the second sense refers to the game of cricket. Now, I go to the hypernym relation. It will show you all the list of basically, I mean, if you try to, there are APIs available for WordNet in many different, like there are Java API available, there are Python API available, even C++ older libraries available. So you could, given a word, you could pull out all the different senses in which it belongs. And then for any sense, you could pull out all its hyponyms, all its hypernyms. Hyponym, typically a concept will belong to one hypernym, because in a tree structure, you will have, that a node has only one parent. But even that is not the case. So I studied WordNet exhaustively during my PhD times. I wrote my own APIs. And I know that a WordNet is not really structured like a tree. There are some nodes which belong to, which has more than one hypernames. Okay, so it is like a graph. It is not really a tree. Anyways, so if you look at the second example, it says that the game of cricket, okay, its hypernym is field game, which is a kind of outdoor game, which is a kind of athletic game, which is a kind of sport, which is a kind of diversion or recreation, which is a kind of activity, which is a kind of act, and so on. Okay, at the very top, for any nouns, you have this very broad concept, which is entity, because every noun is an entity. Okay, so at the very top of this noun subtree or the noun ontology, you have this concept entity. But you can now see how it is becoming useful. Say, for example, I don't know, I give this example in Bengali, but I don't know whether you will understand this. But for example, you want to differentiate whether, take the example of, I don't know, maybe let me think of a, say, I'm just think of a random word like XYZ, okay? Maybe one sense of this belongs to a person, and the other sense belongs to some like object, maybe something like, I don't know, whatever, some object, not a human, okay? Now you need to know whether this refers to, because it will not directly say a person. Maybe it will say, the definition will say that, maybe take the example of lad, okay? Now you know that it is, okay, here it is written that a boy or a man, but you do not know whether it refers to a human, okay, or a person. So if you go into its hypernym tree, in its hypernym tree, you must find a synonym, a synset which contains person. Here you can see a boy is a male or male person. A male or male person is a person. Okay. So then depending on, because you have got this additional, you can say these are like world knowledge kind of a thing. Okay. So if you are using this WordNet as your semantic resource, then you do not just, you can use it as like a machine readable dictionary, but much more than that, you can pull out many additional knowledge from this WordNet. Okay. In fact, say for example, I'm giving you a example in Bengali. Those who are Bengali will understand this example. Say for example, I'm building a rule-based machine translation system. And in Bengali, what happens is, say for example, you have a man, you will translate it to ekjon lok. Okay, so if the noun refers to a person, we typically say ekjon. But if it is a book, then we do not say ekjon boy, we say ekta boy. Okay, so if it is an inanimate object, then we typically say ekta as the translation of a. Okay, so depending on whether the noun is animate or like a person, we should produce the proper translation. Then in that case, you need to know whether the noun is referring to a person or not. Okay, so then WordNet will help you. It can help you in that regard. So in fact, if you want to see, say for example, take the example of hand. Okay, no, not hand, maybe fruit. And if you want to see the different hyponyms, so here you can see all different types of fruits that are fruit, like olive. I think these are all different types of fruits. Okay, so berry is a hyponym of fruit. I don't know, berry should have been an instance of fruit, but anyways, take the example of, say for example, what computer. Let us say computer. I don't know what are the hyponyms given for computers. But a digital computer is a kind of computer. A home computer is a kind of computer. Even a laptop should be a kind of computer. A server is a type of computer. Okay, so these are all like different concepts that all belong to. That are basically hyponyms of computer. Okay. So WordNet also produce some other relations, like we have already discussed about hypernym and hyponym, which basically refers to this superset and subset concept. Then there is called the member meronym and member holonym. Okay, so basically it's a part whole relation. So from groups to their members and from members to their groups. Say for example, member meronym. So faculty is the member meronym of from groups to members. has meronym. So faculty has a professor. You know, a faculty will have professors, assistant professors, associate professors. So faculty is the holonym, I think. Faculty is the member holonym, and this professor is the member meronym. Okay. Similarly, it has the part meronym and the part holonym. Like a table has a leg, so table is the holonym and leg is the part meronym. Similarly, if you see, like say for example, hand. Okay. Now this hand, the first and yeah. So if you look at the meronyms, hand is a part of, okay, you can see hand is a part of arm, arm is a part of man, human being, and so on. Okay, so hands hypernym, or not, it's not hypernym, but holonym, part holonym is arm. Okay, now if you see the meronyms, parts of a hand, you could see the parts of a hand like arteries, and you must have also finger, okay, palm, and so on. So these are the parts of a hand. Okay. And similarly, you can also have the instance relation, which I've already discussed, and antonym relation, and so on. WordNet has many different libraries available. Earlier, it was available in C and C++, but then we had the analytical library, which is in Java. But these days, we also have Python libraries available for WordNet 3.0. And WordNet is the most used semantic resource in natural language processing. There are no resource which is more used than WordNet, at least in the study of semantics. Now, so WordNet is a general purpose ontology, but there is a thing called MESH, which is a acronym for medical subject headings. So it is kind of like WordNet, but it has been developed particularly for the medical domain. So it has been developed by the National Library of Medicine. So it has 177,000 entry terms that corresponds to 26,000 biomedical headings. Okay. Now these entry terms are equivalent to what we call as synsets. So they are basically synonyms, okay, or synonymous concepts in medical science. Okay, and this definition is equivalent to what we saw as gloss in WordNet. Now this is how it looks like. So these are the very top level categories. Now if you expand any category, say for example, if you expand the like, because it is a hierarchically structured data. So if you expand these chemicals and drugs, so these are the different concepts which belong to this concept. Okay, so these are the sub concepts. Then again, you can, if you click on amino acids and peptides, so it has proteins and so on. Okay, proteins has blood proteins, and then blood proteins has these many different types of thing, and every category has a particular tag. So these chemicals and drugs, so I mean, it basically the tag for this is D. Okay, so all these subcategories, they start with this D. Okay, so amino acids and peptides, they have the tag D12. Then proteins is D12.776. Then it is D12.776 dot something. Then hemoglobins, it has also another part appended at the end. Okay. Now, the why MES has been developed. It is a very, very useful resource in both in for the National Library of Medicine for the study of, particularly for searching biomedical related documents. So, so it is indexed in Medline and PubMed. Those of you who works in the medical domain must know about this medical and PubMed libraries, Medline and PubMed libraries. So every paper is indexed in this PubMed database. So it is the National Library of Medicine's bibliographic database. There are more than 20 million journal articles, and this information is very old. Like I'm talking this about at least 5-6 years ago. So maybe there are more than 50 million journal articles by now. Okay, and each of these articles in the National Library of Medicine or in the PubMed have been hand assigned 10 to 20 mesh terms. That is, these such terms, such that if you want to very specifically search about any, say for example, you want to search with, you want to find a paper which relates to COVID, then which relates to medicine, and then which relates to any adverse effects, then you just put these words. There are entries for such words in the mesh hierarchy. And then you will get the exact articles that has been indexed that have those indices. Okay, so this is a very, very useful resource for finding out biomedical related articles. Now in computational semantics, now we go to the actual task. So there are three very well-defined tasks. The first one being Watson's disambiguation. So the very basic task is Watson's disambiguation. When a word has multiple senses and it is used in a particular word, you will have to find out in which particular sense it has been used in this particular sentence. Okay, and it could be either corpus-based approach or it could be thesaurus-based approach. We will look into these approaches. Then another problem in semantics or computational semantics is the task of word similarity. Given two words, you will have to find out a similarity between these two words, particularly useful for like information retrieval and many other applications. And the other task being semantic role leveling. So this particular talk will focus mainly about Watson's disambiguation and word similarity. In fact, I have not included anything on semantic role leveling. So let us focus on these two basic tasks. And semantic role leveling is a very, even I myself don't understand I mean, it is a very complicated linguistic concepts. Okay, so I don't really take interest in semantic role leveling. I should have included something, but anyways, let us understand these very two fundamental tasks: Watson's disambiguation and word singularity. So why required again? Words have multiple senses, and whenever a polysemous word is used in a particular context, you will have to find out which particular sense the word has been used in this particular context or in this particular sense. I mean, if you go to WordNet and if you find with table, I think these are taken from, yes, these are taken from WordNet. So you can see 6 different tables. In fact, the last table meaning is very like, you can see food or meals, like this one, food or meals, I think food or meals in general. Even I did not know that table could refer to this. Okay, so this WordNet, it is a very, very fine-grained, you can think of it as a very fine-grained dictionary. Like it provides many fine-grained senses. Anyways, so we could have many different types of WSD methods. The first of all, you could have, if you are using data-driven techniques, then we could use machine learning based methods. It could be either be supervised techniques if you have training data, or if you do not have any training data, then we could also use some unsupervised Watson's disambiguation techniques. In fact, I have not included sense induction, which is a kind of unsupervised WSD. Maybe I will forget, so I will mention it here now only. So sense induction is a kind of a task where you are given a very large corpus, but you do not have any dictionary. Okay, any dictionary at all. The task of Watson's disambiguation is that you will be given a text or a sentence. Think of it just for a sentence, and the sentence has some polysemous words. Okay, now all these words have multiple entries in a particular dictionary, machine readable dictionary. The dictionary has to be in a digitized format. Okay, say for example, the polysemous word has 2 meanings in that particular dictionary. Now you will have to say, your WSD method have to say in which particular sense, whether the word bank has been used in the financial bank sense or in the river bank sense. Okay, so this is you will have to have a dictionary, machine readable dictionary. But in the unsupervised, or it is not really unsupervised WSD, but in sense induction, what the case is that you are given a corpus but no dictionary at all. Okay, so from this corpus itself, you will have to find out how many different senses are there. Say for example, take the word bank. How many senses are there for the word bank that are found in this corpus? Okay, so it is a kind of clustering. It uses kind of, so what it will do basically, it will find out all the sentences that contains bank, and then it will try to cluster them, and it will see, it might find that there are very 2 good clusters or maybe 3 clusters. Then it will say that maybe bank has 3 different senses, and these are their usages. Okay. I do not have anything covered in this particular slides, but we will talk about supervised techniques, and we will also talk about dictionary-based techniques. So in supervised machine learning-based approaches, you will have to have some training data, and your training data will look like this. Say this particular word is polysemous. So we will have to disambiguate these words. Is So this WSD is the acronym for word sense disambiguation. You will have to disambiguate the polysemous word. So the training instances look like word and its context. Okay, then you will have the level that in this particular context, the word 1 is used in sense 1. Okay. Similarly, you will have multiple such instances of training data. Similarly, you will have for every sense of the word, you will have some instances in the training data that in this particular context, this word has been used in this particular sense. Okay. Your training data will look like this. Then you have your machine learning algorithm, which is trained on this particular training data, and then you get your classifier. Okay, which when I mean, if you give a new instance of this particular word, the same word, okay, if you give a new sentence which contains this particular word, your classifier will then tell that in this sentence or in this context, this particular word belongs to sense J, for example. Okay, so this is how it does it. Now, training data example. Okay, so we have already seen how the training data examples look like. So now, by context, we refer to the surrounding of the word. I mean, you could either think of the entire sentence as the context, or typically what we do is we kind of consider a plus minus n words window. Okay, so in this particular case, you will see we have taken a plus minus 4 words. So 4 words to the right and 4 words to the left. So whatever are the words that are there in this context window, we will use it for the actual purpose. Okay, and in fact, we have seen that bus has 8 different senses in the wordnet, but all these 8 different senses could be like grouped into coarse-grained senses. So if you see, if you consider these brownish or grayish like senses, concepts, sea bass and then freshwater bass and bass, these 3 senses, all of them refer to the fish sense. The rest of the senses, they all belong to the musical sense. Okay. Now maybe we want to group them into just 2 these coarse-grained senses, whether the mention of a bass, it belongs to the musical sense or to the like the fish sense. Okay. Now, most of the supervised machine learning approaches, they require a very simple representation for the input training data. Okay. Typically, it is like vectors of sets of features and feature value pairs. And now our task is to, our first task is to basically extract the training data from the corpus with respect to the target word, then which then involves this characterization of the context word surrounding the target. Okay. Now this is where machine learning and linguistics, or NLP in general, like intersect. Now, if you just choose the raw surface words that appear in the context, and if you use them as features, then most of the burden is on the machine learning classifier. Okay. But if you then, if you decide to do a lot of linguistic analysis, say for example, if you do morphological analysis, parsing, like PS tagging, and then use this linguistically derived informative features, then it becomes a lot easier for the machine learning classifier. Okay. So let us discuss about some of the relevant linguistic features. So first of all, collocation features are information about the words that appear in specific positions to the right or to the left of the target word in the context window. Okay. So let us consider and typically what we do is we do not just consider the words, we also consider their part of speech. Okay. So if you are considering a plus minus n words window, then your feature vector will look like this. So word in position minus n, and the part of speech of the word in position minus n, and so on. And the last feature will be the word in position n to the right, and this is to the left. Minus n basically means to the left. Okay, and the part of speech of the word in position n to the right. So now if you take this practical example, an electric guitar and bass player stand off to one side, not really part of the same. And if we stick to plus minus 2 words context window, then your context window will look like this: guitar and player stand. Okay. So then if you only consider collocation features, your feature vector will look like guitar, its part of speech noun, and its part of speech, this is conjunction, and then player, noun, stand, verb. Okay. So this is how your collocation feature vector will look like. But collocation feature vector are not very useful. So we use co-occurrence features. So which basically gives us information about the words that occur anywhere in the context window, not in specific positions. We will not say that what is the word that is exactly 2 positions to the left or exactly 1 position to the right. We will not ask this question. We will just ask whether this particular word appears in the context window or not. Okay. So in this, what we do, typically we find out K content words that appear most frequently in the context window of the target word. Okay. So we will analyze all the sentences in which the target word appears, and then we will consider all its context window, and then we will consider the words that appear in this context window and their frequencies. And from there, we choose these top K content words. Okay. Then what do? We do not consider this word raw words. So what we instead do, we consider their counts or as the feature. Okay. So we will see how many times phishing appears in the context of a particular instance of the word boss in a sentence. Okay. Now, if you look at this practical example, say this is your training data. This is one instance. And if you take this, or maybe you are trying to classify which particular sense this word belongs to, this bus belongs to in this sentence. So then if you consider a plus minus 2 words window, then your context window has the words guitar and player stand. And then your co-occurrence feature will look like this. Okay, so it is a vector of 10 because you have considered 10 most frequent words that appear in the context window. And then, so you can see that I think 4th word is the player. Okay, so player appears only once in this context window. And similarly, guitar, I think, is the 9th feature. Okay, and its frequency in the context window is 1. Okay, so this frequency is the frequency of the co-occurrence word in the context window in this particular instance. Okay. So now if you look at the collocation features, the training set will look like this. I mean, the training set consists of training instances, and from these training instances, what you will do, you will convert the training data into basically feature vectors, every instance into feature vectors. So this is your first collocation feature vector and so on. Okay. And these are the corresponding co-occurrence feature vector, where every word, I mean, every instance has this label at the end. So this last 0 basically says that this instance belongs to the musical sense of bus. Okay, so this 0 denotes the musical sense, and this particular instance belongs to the bus fish sense. And so is the case for the co-occurrence features. And finally, when you will have the given a new sentence that contains this particular word. So that was the word. I mean, that was the sentence we are trying to disambiguate, this one. Okay. So its collocation features looks like this, and its co-occurrence feature looks like this. And finally, given this, it will hopefully predict the correct output. Okay. Now, given this training data and given that you have extracted the co-occurrence features and the collocation features, then you can use many different types of supervised machine learning algorithms like naive-Bayes or decision trees or neural networks or SVMs or k-nearest or all these different types of ML approaches that are available. Okay, and if you train these algorithms on this particular data, then you will get the corresponding classifier. Now, I do not have the scope for going into this like different types of like classifiers, but I will just have a slide on naive-Bayes. I will just explain how you can do this using naive-Bayes. So you know that, okay, so let us consider this V is the feature vector, I mean, given a new instance of the particular word. So you have already defined your feature vector set, okay? I mean, feature set. So you convert this test sentence into the feature vector. Say the feature has, I mean, you say you have considered n features. So there V1 to Vn. Then this small s is a sense of the word, okay? Where this capital S is the set of senses of the word. Say if you, for example, you take the word bus, it has 2 different senses. So this small s1, it refers to the financial, I mean, one sense. I mean, if you think of s1 and s2, So S1 refers to the financial bank. Let us consider, and S2 belongs to the financial bank. I mean, sorry, the river bank, second one. So then we will have to compute this probability of S1 given B and probability of S2 given B. How likely is that given this feature vector? What's the probability of S1, the first sense, and what's the probability of second one? Okay. So for whichever S, this probability is higher or maximum, that sense will be assigned as the like most likely sense, or the maximum a priori sense. Okay. Now you know that using Bayes rule, this can be converted as this, simply applying Bayes rule, because if you multiply this with the denominator, and if you take the product of the the numerator part, in both cases you end up with the joint probability of S comma V or B comma S. They are both the same thing. Okay, so you can simply use the Bayes rule and get this equation. And this argmax basically says that for whichever argument maximizes this whole thing, maximizes this function, will be returned. Okay, so it is not the max value is returned, but instead for whichever argument this thing is maximum, that argument is returned as the output. Okay, and because the input sentence is given, so the input sentence has been converted to the feature vector, and the feature vector is a fixed feature vector. So in this part, what changes is S. Okay, B remains exactly the same. B is the feature vector. Okay, so this probability of B, whatever it is, it remains the same. So you can simply ignore from this equation the denominator part. I mean, you can think of PV as like a constant normalizing factor. So the thing is, the logic is, whichever S will maximizes the numerator will also maximize this whole thing. Okay, and simply ignore this denominator part. But then now we have converted, we started with probability of S given B, but now we have ended up with probability of S. How likely is the sense itself? So this is called the prior probability, because you can compute this probability before looking into the test sentence. But now we are ending up with probability of B given S. Okay, so this is a complicated concept. What's the probability of the feature vector given S? Okay. Now, I mean, if you really want to, because you know that B is essentially B1, comma B2, comma N. So, if you expand this using the chain rule, this will look like probability of B1, comma S times probability of B2 given S, comma V2 times probability of B3 given S, comma B1, comma V2, and so on. Okay, but then to make things simpler, we make a simplification assumption. We make the independence assumption, which basically assumes that features are independent of each other. And if that is the case, then you can simply compute probability of B given as the product over I, probability of individual features given S. Okay. Now, if you make this independence assumption, then it makes the computation so much simpler. Okay, and we can very easily compute this from the corpus, training corpus. So by this combining these two, that by using this, making use of this independence assumption, and by reducing this denominator part, we arrive at this final equation. So S hat, which basically means that the assigned sense or the most likely sense, is for whichever argument S, whichever sense it maximizes this part, the probability of S times product over J, probability of Bj given S. Whichever sense maximizes this thing is returned as the most likely sense. Okay, so the Bayes is a very simple algorithm, and one of the very basic algorithms, but it is often used as a very standard baseline. Okay? And in fact, if your features are independent of each other, then you are not making any simplification assumption, because this is already true. And this is then the perfect, in fact, this is not, this should have been the approximation, okay? Like this one, not exactly equal, okay? But then it becomes, this is the exact formulation. If the independence assumption is true. But because features will not be independent of each other, so they will depend on other features, okay? So this derivation of Bayes is not actually true. So that is why it does not perform very well. Now, there are many issues with, say, for example, you don't have enough training data. So for that, what you can do is you can use bootstrapping techniques. So for example, you start with your small training data, which is typically called the seed data. Okay. And you apply your machine learning algorithm, whatever machine learning algorithm, supervised machine learning algorithm it is. You train your machine learning algorithm on this particular training data, and you get a classifier, which is not supposed to be very good because you have trained it on a very small amount of training data. But then you use this classifier on a raw data in which you do not have, like in every sentence, you do not have the corresponding label assigned. So it is not labeled training data. For supervised machine learning, you always need labeled training data. Okay, but you apply this classifier on this raw data to derive their labels, basically to assign their senses. Okay, so in this way you get more classified data. Okay, I mean, you can assume that if this classifier is 60% accurate, then you can guess that 60% of this classified data is correct. But you can use this classified data, which is kind of noisy training data. You can simply add it to the this training data, and you again train on the machine learning classifier, and then you build a new version of the classifier, and so on. So this loop goes on. So in this way, the classifier becomes much more and more confident, because you are reading. I mean, it might be with somewhat noisy training data, but nonetheless, you are training your model on larger training data, and it will be even better if you look at this training data and if you manually correct the wrong ones, because these data has been already labeled. So if you start to label it from scratch, it will take some time, but it will take much less time to correct the wrong labels in this classified data. Okay, so then if you correctly, I mean, if you employ some human or linguistic expert to correct the wrongly classified data, then very easily you could get more and more training data. Okay. Then this was about how you can use the corpus-based methods or for supervised machine learning. Then dictionary and thesaurus. I can see some comments, but I cannot really. I am not focusing on the comments really. So what I will do, I will try to finish the lecture by like 1 hour 40 minutes or something like that, and then last 15-20 minutes I'll try to take the questions. And I know during the talks, if you ask me the questions, that will become clear then and there, but that will hamper the flow of the lecture. I can take questions, but it is up to you. It is up to the organizer whether.
Sir, we allowed in earlier video means lectures, we allowed participants.
Yeah.
But sometimes people miss, and then lot of background noise starts.
Yeah, that is the problem. It hampers the flow of the lecture. That is the problem.
Yes, that's why
But I have slide numbers. So if you have a particular question on a particular slide, just note the slide numbers, and then you can tell me, sir, please go to this particular slide. I have a question on that slide. So I'll go there. Okay.
So to all participants, sir will have sufficient time to resolve your query.
Yeah,
Okay.
I'll try to.
Okay, sir.
So LASK is a thesaurus-based method. It is a very old method, and so it was proposed by a linguist named LASK. So he basically said that choose the sense whose dictionary gloss basically means the dictionary definition. So if you go into any dictionary, so it will provide you a short description for that particular sense. So that is called the gloss. Okay. So choose the sense whose dictionary gloss share the most words with the target words neighborhood. So given a new sentence, look at its context, maybe look at the entire sentence and find out how many words in this particular context appear in the dictionary gloss. So if you have two different senses for a particular word, then you have two different gloss. Okay. And whichever gloss shares most number of words with the context, you will say that in this particular context, the word has been used in that particular sense, corresponding sense. Okay. And typically when you do this, we do not include the stop words. I mean, stop words are in general like excluded from any kind of processing. I mean, not from previous taking or parsing, but for when you are doing any kind of numerical analysis, like when you are considering the frequency information, you do not typically consider them. Then here is an example. I mean, this is not a very good example, but nonetheless, so I think this is taken from WordNet. Now check channel. Yeah. So channel has many different senses. Channel refers to the small streams. In this particular case, it refers to the small stream next to the streets. And the other sense is TB channel, but you could also have, like in hospital, they make a channel in your body to pass the fluid, so on. But even if you consider these two ones, so you will look at the context and then you'll see how many words overlap with the corresponding. So this is the dictionary gloss, a passage for water up till this. Similarly, a television station and its program. So this is the gloss. Okay. So whichever gloss shares the most number of words with the context, you will say that this is the intended sense in this particular sentence. Now we will go into the second task, which is the task of finding word similarity or sense similarity. We'll start with sense similarity, and then we'll see into how we can assign similarity between words. So word similar, okay, now we have already discussed about synonymy. Now synonymy is a binary relation because two words are either synonyms or not. Okay, so you will say that boy and lad, they are synonyms, but boy and cricket, they are not synonyms. Even boy and girl, they are not synonyms, even though you know that boy and girl, they are very close concepts or close words. Okay, so similarity is a kind of loser metric. It is not a binary metric. It is a kind of like a range metric, or you can think of a fuzzy scale. Okay, so two words are more similar if they share more features of meaning. So similarity is properly a relation between senses. Okay, so first we will compute similarity between senses, and then we'll go into similarity between words. So the word bank is not similar to the word slope. So we will say that the first sense of bank, which refers to the financial bank, is similar to the third sense of fund. In fact, if you look at the different senses of fund, it has many different meanings, and that only the third sense is the investment company. Okay, I don't know. Even the first sense is the monetary fund, but anyways, I think this is just an example. We will always compare similarity between senses. Similarly, we'll say that the second sense of bank, which refers to the river bank, is similar to the fifth sense of the slope, which refers to the the inclined land or whatever. Okay, but we will compute similarity later over both senses and then words. So why this is useful? This is a very, very fundamental concept in across many different NLP applications to find similarity between words, or then to find similarity between sentences, and then you can broaden this aspect, and then you can find similarity between documents. But if you have a way of finding similarity between words, then you can go beyond words and sentences. Okay. Now, if you think of say for example, information retrieval or web search. Say for example, I search with soccer World Cup. Okay. And now in this part of the world, at least in the subcontinent, football is referred to as football, but in if you go to UK, they call it soccer, not football. Okay, in large part of the Europe, it is referred to as. In fact, they also call it football. I used to stay in Ireland, and they have a game called football, which is played both by hands and legs. Okay, so football there is a completely different game. Okay, it's like rugby kind of a game. Okay, but then you will have to know that soccer is a similar concept. I mean, it may not be exactly synonym to football, but soccer is a very close concept. It has very high similarity with football. If you know this, then you will be able to go into all those documents and explore them, which contains football and not soccer. Okay, because I expect that most of the documents will have football in them instead of soccer. Okay. So it is similarly in all sorts of application, like question answering, information extraction, and all sorts of, if you think of plagiarism detection. So say for example, I plagiarize a paper. I have a paper. I have say for example, I have done some research, but then while writing the paper, I take a lot of copying from an existing paper, particularly for the literature work. Okay, but because I'm intelligent, what I do is I replace the words with the synonyms, or I tweak the structures of the sentences so that the authenticate or any plagiarism detection tool gets pulled. In fact, I checked. I mean, I was having an interaction with the authenticate guys. So we had a team of authenticate people coming over to university. And I was surprised to know how naive is Authenticate. It is a very, very naive text similarity tool. It is very easy to fool Authenticate. Okay, but if you have a proper text similarity detection tool which can find similarity between synonymous or similar words, then that will do a very good job of plagiarism detection. Okay. Okay, so again, we come to two different concepts, word similarity and word relatedness. So we obtain distinguish word similarity from word relatedness. So by similar words, we will refer to near synonyms, okay? So we will say that cars and bicycles, they are synonym, maybe cars and motors, so they are also like similar concepts. But cars and gasoline, they are, although they are very similar, you know that cars runs on gasoline, okay? But one is like I mean, car and gasoline is a liquid, car is not a liquid thing, okay? So they are very dissimilar in that sense, but they are related because car runs on gasoline. You cannot separate gasoline from car, okay? So word similarity and word relatedness. Then we will consider two types of algorithms. So the first one is dictionary-based or the thesaurus-based algorithms. And in these algorithms, we will try to see whether the two words or two concepts, they are nearby in the hypernym hierarchy. If they are very close to each other in the hypernym hierarchy, then it must be the case that they are very similar. But if they are very far in the hypernym tree or in general in the ontology, then their synonymy, I mean, their similarity is less. Okay. Or if you consider the LESC method, do words have similar glosses? If you say, for example, you are trying to find out the similarity between two words or the senses of two words, then what you can do is you can find the similarity between their glosses. How many words overlap between their two glosses, and that could give you an indication of the similarity between the two words. And then we will discuss a very interesting kind of algorithms, unsupervised algorithms, so which is called distributional algorithms. So there we will try to look into whether two words appear in similar kind of context. Okay, so we'll look into that, yeah. So first, dictionary-based approaches. So first, path-based similarity. So let us consider that this is our WordNet ontology. Okay, so this is not the entire ontology, but we have only put the words that are of to our interest. And we will say that two concepts or two senses. So each node refers to a scene set. Okay, although you see only one word, think of it as an entire scene set, WordNet scene set. So two concepts or senses or scene sets are similar if they are near each other in the thesaurus hierarchy. Okay, so that basically means that if they have a short path between them. Okay, and we will say that concepts have a path of one to themselves. Okay, so that is why you see that the path between nickel and coin, you will see it is 2, but there is a reason. I will come to that. Why this? I mean, typically, if I ask you the question, what's the distance between nickel and coin in this particular graph, you will say that it is 1. Okay, what's the distance between nickel and dime? You will say that it is 2, but just add 1 to it. Okay, so if I ask you what's the distance between nickel and nickel, your answer should be 0. But for this particular method, think of the case that distance between a node and itself is 1. Okay, so you will add 1 to everything, all the distances. So then path length is defined as 1 plus the actual number of edges in the shortest path in the hypernym graph between census nodes C1 and C2. In fact, you will see that if it is not a tree, I mean, if it is a tree, then it will not say shortest path because there exists only one path between any two nodes. Okay, but because the ontology may not be a tree, it can be a graph. Sometimes there are some loops. Okay, very rare, but there are some loops. So we'll consider the shortest path. And the similarity should range between 0 to 1. Okay, and the path similarity is defined as 1 over the path length between C1 and C2. So if we want to compute the similarity between the two concepts C1 and C2, then we will first compute the path length between C1 and C2, which is 1 over the actual number of edges between the two nodes C1 and C2 in the ontology or in the graph, and then take the reverse of it. Okay, now if I ask you, okay, according to this method, if I ask you what's the similarity between nickel and nickel, okay, now like I said, so the similarity should range in the scale of 0 to 1. So if the words are completely dissimilar, you should assign it a score of 0, and if they are exactly similar, that is the same word, you should assign it a score of 1. Okay, now if I now ask you the question of what's the similarity between nickel and nickel, okay, so then their path length between nickel and nickel is 1. Okay, so it becomes 1 over 1, which is 1. Okay, so it becomes the maximum similarity score. So it takes care of two different problems. So this plus 1 it takes care of two different problems. First of all, you can now compute the similarity between a node and itself. Otherwise, it would have been infinity. You cannot compute this 1 over 0. And secondly, it restricts the similarity score to 1. So the maximum similarity score will be assigned is 1. It cannot exceed that. Okay. And then we can, so this is the similarity between path-based similarity between two concepts, C1 and C2. Then based on this, we can assign this word-based similarity, W1 and W2, as, so it is like this. Think of the case, say this is W1 and this is W2. And let us consider this W1 has two different senses, S11 and S12. And W2 has three different senses, S21, S22, and S23. Okay, I'm not writing down. But what we will do, we will compute the similarity score between every pair. In this particular case, 6 pairs. Okay. So for all senses of S1 belonging to senses of W1, and for all senses of S2 belonging to senses of W2, we will compute the similarity score between the sense pairs. Okay. Then whichever sense pair, whichever pair has the highest similarity, we will assign that score to the particular word. I mean, we will assign that, but say this is the highest similarity score, this thickened line. Okay. So whatever is the score, we will assign this score as the similarity between the word. Why? Because, so I mean, first of all, look at the derivation. So if you want to compute similarity between the words W1 and W2, you will consider the similarity between all the senses of C1 such that C1 belongs to the senses of W1 and C2 belongs to the senses of W2. You will compute the similarity between all such pairs, C1 and C2, and whatever is the maximum similarity among this, you will assign them as the similarity between W1 and W2. Why do you think so? Because say, take for example, I ask you the question, what's the similar, I want to know how similar is the word cricket to the word football. Okay. Now you know that in both the cases, the word football has two different senses. One refers to the game of football, one refers to the football as the object. And you know that cricket has two different senses. One refers to the game of cricket and one refers to the like insect. Okay. Now, when I ask you the question of what's the similarity between football and cricket, what immediately comes to your mind, I am talking about the game sense of football and cricket, right? So that is why you should return like the similarity between football as the game and cricket as the game. Hopefully that will return you the highest similarity, because you can see that football, I mean cricket as its direct, I mean the second sense, as its direct hypernym, you can see this field game. Similarly, if I take football, so you can see as its direct hypernym, you can see this field game. And similarly, I mean, if you think of like say this is the football, okay, football 2 or whatever, football 1, or say this is the cricket 2. Okay, these are the two game senses. So they have a common parent, which is the outdoor game, and then all their ancestors are the same. Okay, so they should have a very high similarity. Okay, because I mean, in this particular case, the similarity should be 1 over 3 according to the path-based similarity, because actual graph-based distance is 2, so 1 over 3. Okay, which is not a very high score, but we'll look into the other methods that will hopefully assign a better score. But the point is, the other pairs will be assigned more, even less score, maybe 1 over 13 or 1 over 15, which is much less than this 1 over 3. Okay, so this score will be returned as a score between the pair of words. Okay, now path-based similarity, if you look into, I mean, if you try to figure out the path-based similarity between pair of words, so nickel and coin, 1 over 2, because the path length is 2, and so on. So now, if you look at the similarity between nickel and money is where money, so the length is 6, and this coinage and Richter scale, so this Richter scale and coinage, this term, okay? So they also have a path length of 6. So that is why the similarity between nickel and money and the similarity between coinage and Richter scale are assigned as both as same, okay? But this is the problem with path-based similarity, because you know that nickel is very similar to money. Okay, in fact, I mean, by nickel we do not refer to money, but in many foreign countries, nickel often referred to coins. Okay, so you know that nickel is a very similar concept to money, whereas coinage is a very far concept from Richter scale. Richter scale, as it is used for measuring earthquakes. Okay, so coinage has nothing to do with earthquake, but still you are getting the same score, similarity score according to the path-based similarity. So the thing is, nodes high in the hierarchy are very abstract. Okay, so because we are, I mean, in case of nickel and money, we are taking this path, and in case of coinage and Richter scale, you are going through this path, this higher path. Okay, and so what we want instead is a mechanism or a metric that represents the cost of each edge independently. That is, we want to have a weighted graph. We want to assign like some kind of weights to each path. Okay. So why? Because words connected only through abstract nodes, they are very less similar. So if I ask you the question from this slide, what's the similarity between currency and money? You know that there is a short path, like only two edges. But if I ask you the question, medium of exchange and scale, okay, although they have according to the graph-based approach, I mean, they have two edges in between them in the shortest path. They are very broad concepts. Okay, so they should have very less similarity. So lower nodes in this graph should have higher similarity than the nodes in the higher in this graph. Okay. So we go to this information content-based similarity, so which was introduced by Resnick in 1995. So let us try to define probability of C, probability of a concept. Okay, so the probability that, I mean, probability of a concept basically means that, say for example, probability. Well, first, let us consider probability of a word. What does it mean? It means that it assigns a probability. I mean, we will later go into how we can compute this probability, but probability of a word basically means, say I have a newspaper, or say I have a book in my in front of me. I randomly, blindly turn a page. I randomly take my pen and I take my pen and randomly put somewhere in the page. I put my pen. If I say probability of the is in English is something like 1/7. Okay. So something like 0.15 or something like that. So that basically means that word, which is, over what my pen is, that word, the probability that word is the is 0.15. Okay. Just like that, probability of a concept means what's the probability that a randomly chosen word belongs to this particular concept. Okay. So the probability that a randomly selected word in a corpus is an instance of concept C. So all the words are the members of the root node. So you know that in the noun hierarchy, the top node is entity. Okay. And every noun is an entity. So every noun has the entity node as an ancestor. Okay. So because every noun is an entity, so the probability of root is 1. Just think of the noun hierarchy. In fact, in the word net, you have separate hierarchy for nouns, separate for verbs, and separate for adjectives, because the same relations are not available for all the part of speech. Okay. And the lower a node in the hierarchy, the lower its probability. Because you know that if I ask you how likely is this word being an entity, that answer will be very high. If I am only talking about how likely is a particular noun being the concept entity, that answer is 1, because every noun is a concept. Okay, but the lower you go, you get more and more fine-grained sense. So the probability becomes less and less. The probability of the concept. Okay, let us take this snapshot into account: entity, geological formation, and so on. Now, how we compute this probability of concept? We train by counting in a corpus. So each sentence of hill is here. Okay, each sentence of hill counts towards the frequency of natural elevation, geological formation, entity, etc. So each instance of hill will count towards all its ancestors. Okay, sorry, this one, like natural elevation, geological formation, and its parent up to entity. Okay. So let's word C be the set of all words that are children of node C. Okay. So word C, not children, I think it is it should have been the what it is called, predecessor. Okay. So word C is a set of all words that are predecessors of node C. Okay. So then you will basically, for the geo information for this particular word, the bag will consist of all the nodes, all the words that are rooted in this particular node, in this subtree. Okay. So all its predecessors will become a member of this set. Okay. Similarly, words natural elevation, it considers hill, ridge, and natural elevation. I don't know, in this particular slide, it does not show the root, but it should also consider the root. Okay. And then finally, by the probability of a concept is measured as how many times, basically, how many words do you have in this particular set divided by how many words do you have in the corpus. Okay. So that is how you can get the probability of a concept. And then, so Deccan Lin showed that, he provided this study and he found out the probability for a snapshot of the hierarchy, entire hierarchy. Now we can see that the probability of the entity is 0.395. I earlier said that the probability of the entity is 1, or the root is 1, but here it is showing as 0.395. The reason being, he considered all the words. Now all the words are not nouns. So this basically says that 39.5% of the words in that particular corpus are nouns. Okay, that is why the probability of entity in that particular corpus is 0.395. But the important thing to be noticed is that more you go down towards the bottom of the tree, the probabilities become less and less. And then information content, which is a concept in information theory, is defined as information content of a concept is defined as negative log of PC. Okay. So we want, the most informative subsumer is the lowest common subsumer, if you look at the picture, so say you are trying to find out the similarity between F1 and C2, whatever is this and this. So this is their lowest common subsumer, the lowest ancestor. Okay, they are all subsumers. They all these concepts, they subsume both F1 and C2, but this is the lowest in the hierarchy. Okay, so we will say that this is the most informative node when we are describing about F1 and C2. Okay, so we will take into consideration the information content or the probability of this particular node, the LCS, lowest common subsumer. Okay, and its information content. So reasoning similarity is defined as simply as the negative log of P. Basically the information content of this LCS of C1 and C2. Now we know that information content basically means negative log of PC. So it is negative log of P probability of the LCS of the C1 and C2. So this is how reasoning similarity is measured. Now, Deccan Lin proposed an advancement over this method. So he basically said that the similarity between A and B is not just what they have in common, but it should also depend on how much they differ. Okay, so the more differences between A and B, the less similar they are. Okay, now I will give you an example like say I ask you this question. So you have this pair of, you have a pair. Say this is AB. Okay, think of them as sets, and you have another pair. Maybe I will say maybe I'll okay. This is one pair, A and B, and this is their intersection. Okay, A and B, and this is another pair, C and D. Okay, and let us assume that this intersection is common, like this part, the area of this intersection is common. So if I ask you the question of A intersection B, the area of A intersection B and the C intersection D, they are common. But if I ask you which pair seems to be more similar, the answer should be AB, because they have less difference. Okay, you can see this is the differing part. C has a lot, C and D has a lot which is not common to them. Okay, so we should also consider these differing parts. That is the principle of, that is basically the idea behind the lean method. So we will take into consideration the commonality part, which is measured by the LCS, but we should also look into the differing parts. Okay. Now, how can we get the difference? So if you, if I ask you the question, how can I get the the area of this? So if you simply take A union B, and if you do A intersection B, you will get the difference, right? So A union B gives the entire thing, and then you are subtracting this thing. So that is when you are get this differing part. So the commonality part is is obtained by the intersection, and the difference part is given by the description. Description is obtained by the union, and then you subtract the commonality part, which is the intersection. In fact, the lean similarity is proportional to the commonality. So because more similar there, more area of this intersection, the higher the similarity. And the more dissimilar there, the more have they different part, it should be penalized. The more dissimilar there, okay, the larger this area is, the more dissimilar there. So it is inversely proportional to the description. In fact, lean similarity is defined like this: 2 log of probability of the lowest common subsumer of C1 plus C2, C1 and C2, and the description of C1, which is the negative. Actually, this is information content of C1. Here is a minus, here is a minus, and here is a minus, but the minus cancels them out. Okay, and you might ask why these two? Because again, if you have the same concept C1 and C1, if you are trying to find out the concept between C1 and C1, then this is log of PC1 plus log of PC1. So this is essentially 2 log of PC1. And in the numerator, you have 2 log of PC1 because the LCS of C1 and C1 is also C1. Okay. So then it should be 1. Okay. If you take 2. This is just an example. If you try to find out the similarity between hill and coast according to lean similarity, it will come to 0.59. Okay. But for that, you will have to have this probability of the concepts. Gian conduct similarity, it is also like a similar kind of a concept. So they consider similarity like this. So this is the common part, 2 into this. So the formulation is very similar to the lean similarity, but it is defined as the 2 log of PC, this minus their description part. Okay, so this is one of the best similarity, at least the thesaurus based and corpus based. Now, extended less algorithm, I already gave this example. So if you are trying to compute the similarity between 2 words, you will just look into their glosses and then how the overlap between that. Okay, I have 15 minutes more, so I will not go into the I will just want to show you some. I don't want to miss the most important part. So yeah, so there are problems with both these dictionary-based methods as well as the corpus-based methods. Not the corpus-based, but particularly the ontology and semantics. Dictionary-based methods, because first of all, we do not have a thesaurus, particularly machine-readable dictionary for every language. And even if we do, we have problems with recall because many of the words are missing, many of the senses are missing, most of the phrases are missing, and so on. And if you do not have a particular word in your dictionary, then you cannot find the similarity involving this word with any other word. Okay. So we have distributional models of meaning. It is also called vector space models of meaning, and it offers higher recall. Also, they tend to offer lower precision. And the idea behind distributed models of meanings is that oculist and this is a very old idea. Selig Harris was a linguist. He said that oculist and eye doctor occur in almost the same environment. So if A and B, they have almost identical environments, we might say that they are almost synonyms. In fact, there is a famous quote by Firth that you shall know a word by the company it keeps. So that basically means that in the context it appears. Okay. So here is an example of how it works. I hope none of you know this word Tesguino if you have not earlier studied about this distributional semantics or NLP in general. Okay, even I did not know this word when I first encountered this word. But let us have a look at some example sentences. Okay, a bottle of Tesguino is on the table. So you know that, immediately know that test guino is a liquid. You are not sure anything about whether this is a drink or this is some other liquid. You don't know, but it seems to be a liquid. Okay, everybody likes test guino. Now it seems like it is a kind of drink, some kind of drink. Okay, otherwise why would people like it? Then test guino makes you drunk. Now you know that test guino is an alcoholic beverage. Okay, we make test guino out of corn. So now you know that test guino is a kind of like a, I don't know, maybe beer kind of a thing, which is made out of corn. So just a minute ago, you did not have any idea about test guino, but just by looking into these 4 sentences, you have a pretty good idea about the word test guino. Okay, so we look into the context of the words in which it appears, and then from there we can derive its sense. There is a concept called term document matrix in information retrieval, where the entire data set is represented in terms of the term document matrix, where the rows corresponds to the terms, that is the unique words, and the columns corresponds to the documents. Okay, and these are the term frequencies, the TF of T, term T in D. Okay, all these cells. So this basically says that in this particular corpus, fool appeared 37 times in this novel as you like it. Okay, so this is a concept in term document, and this column vector is called the document vector. This is a count vector. In N stands for natural number, and B is the size of the vector. B is actually the vocabulary size, the number of unique words in your corpus. And now if you look into 2 different term vectors, and if you try to find out their similarity, just by taking into consideration the document vector of these 2 documents, you can perhaps say that these 2 documents look pretty similar. Among these 4 documents, the similarity of terms in these 2 documents are pretty similar. So they should have a high score, similarity score. Now, each word, if you think of a row, each word is a count vector in ND. Okay, so this, this we call this the term vector. Okay, and 2 words are similar if their vectors are similar. If you look at this distribution of these 2 word vectors, okay, you can see that perhaps battle and soldier, their vectors look pretty much like the same. I mean, if you try to find out the vector similarity, their similarity will come out as pretty high. Similarly, fool and cloud, you know, I mean, by looking into these vectors, you can understand that just by taking the vector similarity, you will get a pretty good score. So, and in fact, you know that battle is pretty close to soldier, and fool is also a similar concept to clown. Okay. Now, instead of taking the entire document, we consider a lower context. So typically we restrict our context to paragraph or like plus minus 10 words. So here are some examples of, these are just some snapshots. So apricot, pineapple, digital, and information. We want to consider their similarity, okay? So this shows only the 10 words to the left of the target word and the 10 words to the right of the target word, okay? And from this, we compute what we call this term context, term context matrix, okay? So in this, earlier we had the term document matrix, but now what we have is a term context matrix, where the rows corresponds to the terms, but the columns corresponds to the context words, okay? These are the context words. So it basically says that digital appears 2 times in the context of computer, or the vice versa. Computer appears 2 times in the context of digital, okay? So this is the context. This is the idea of term context matrix, which is borrowed from the idea of term document matrix in information retrieval. And now then if you compute the similarity, I mean, you will get a pretty good similarity, high similarity score between apricot and pineapple. And similarly for digital and information, you will get a pretty good score. So that tells you that apricot has high similarity with pineapple, whereas digital has high similarity with information. But if you take the similarity between information and apricot or pineapple and digital, you will not get a high similarity. I mean, we will get a very low similarity. Okay, that is what is desired. So in the term document matrix, we have a concept called TF-IDF. So we already discussed about the term frequency, and there is a concept of inverse document frequency in information retrieval, but that is not required in the context of semantics. But what we do here instead, from term frequency, we go to the TF-IDF values, okay, which is real, which is like floating values, real values. But here we consider positive point towards mutual information, or PPMI. The idea is the point-wise mutual information is a concept in information theory, and it basically gives you a measure of how likely is that X and Y co-occur more than by chance. Okay, so it is measured as the PMI of X is measured as the log of probability of XY, that is the joint probability, divided by their individual probabilities. Now, if you think of XY as words, you can find out the PMI of word 1 and word 2 like this. You just replace X for word 1 and Y for Y2, okay? And then you compute the PMI. That will give you the, how likely is that word 1 appears, co-occurs with word 2, as opposed to they appears by chance, okay? And then the PPMI, you just replace the, if the PMI values is less than 1, then you will, for this log, you will get a negative score. So we just replace all the PMI values with zeros. That is your positive PMI or PPMI. Okay. So you have this contrast matrix. From this, you compute the these joint probabilities for these values. And for the terms, we compute this PI star, basically the row sum divided by the entire matrix sum. And this, for this column words, we compute the column sum divided by, it's basically the probability of the context word. It's obtained by the column sum divided by the entire matrix sum. And the joint probability of your words like digital and computer. You'll take 2 divided by this entire matrix sum, okay? So
Yes,
then
sir.
it will look something like this. This is your term context matrix. Then if you compute the scores, I'll finish it within 2 minutes, okay? It will look something like this. And then from there, if you compute these are the probabilities, okay? So these are the joint probabilities. These are the probability of the context words, these ones, and these are the probability of the terms. You need 3 things, Pij, Pi star, and Pj star, okay? And then finally, if you compute the probability, if you want to compute the PMI of information and data, this one. So log of 0.32 by 0.37 into 0.58, okay? Whatever that is value is. So it turns out to be 0.58 or 57. Okay. In this way, we will compute all the PMI values and finally it will look something like this. Okay. So you cannot compute it for 0 scores because the numerator is 0. You cannot take log of 0. But if you have any non-zero scores, negative scores, you replace it with a 0. Finally, your PPMI values look like this. Finally, you will measure these are called PPMI vectors. Okay, if you take an entire row, these are PPMI vectors. Finally, you will compute the vector similarity between these PPMI vectors, and that will give you your similarity score. Okay, I had some other slides, but I've covered the majority of the part. So at this point, I think I can end this talk, and I can take a few questions if you have any.
Yes, sir. So
Yes.
that
Go ahead.
co-occurrence and PMI is same.
Yes. No,
Yes.
co-occurrence means the number of times it appears, it co-occurs in the context of a particular word. Okay.
Okay.
Now, yeah.
And PMI means anywhere in the text it will appear. Is it like that?
No, PMI is a information theoretic measure. Okay. Co-occurrence is just the number of times a word appears in the context of another word. But PMI is a measure which is computed like log of Pij. This is the formula. So this is a information theoretic measure that is studied in information theory. Okay, information and coding theory. It gives you the probability. How likely that 2 events co-occur more than by chance. Okay, because sometimes 2 occurs even though they are unrelated, they occur just like I gave an example of TV, and like in that particular example, it is very difficult to, I don't know whether I can look at this one. We have to minimize it or what? Yeah, maybe minimize it. Yeah. I gave an example of TV. I don't know. Let me search. Yeah. And then I think the next slide. Yeah. In this slide, you will see that in this context, you have semantic similarity. Did it go? Yeah. In this particular sentence, you will see streets, channel, rain, all appearing in the same sentence. Okay. Now these streets, now which is in the channel, which is in the definition of channel, you can say this street. Okay. This street is a misleading word. Also, these has no chance of appearing in the context of TV, but this just appears by chance. Okay. But whereas like TV station, channel, these are very like highly likely to appear as a whole. Okay, so that's it gives that probability that how likely is it that it appears as a co-occurring word as opposed to some independent events, some independent words. It gives you a measure of that. It is measured from the probabilities.
Okay. And one more thing in the context of this computational linguistic,
Yes.
will you please explain that graph and tree means what should be called as graph and what should be called as tree? Where
I
graph
mean,
should be
that's
considered?
okay. So I mean, it's a very fundamental concept in data structure. I mean, a graph is a tree is always a graph, but a
Yes.
graph may not be a graph. If there is any cycle, so this is a tree, this is also a graph, okay? But if you have this connection, then this is a graph, this is not a tree, okay? In a
But
tree,
this
you
can
will
be
have only
acyclic,
one.
no, sir. This can
Yes,
be
sorry.
directed acyclic also, no?
No, I mean, it is not really like a directed tree or okay. I mean, since there are relations, you can think of it as directed tree, because if you say, for example, this is A, okay, and this is B, its children, and this children is hypernym relation. This relation is hypernym. Sorry, hyponym. Okay? Maybe hyponym. Okay. So we call that B is a hyponym of A, but you cannot call that A is a hyponym of B. So it is a kind of directed relation. Okay. So all the relations are directed. I mean, you cannot go both ways. But I mean, it's not the same as like the concept of like weighted graph, where like think of a city map where you have distances between two cities, but it is not that kind of a thing. It is a directed graph. Yeah, in that sense.
So graph, if you take directed,
Yeah.
that direction you can mention only in graph.
No, but even in trees, yeah. So that is why I said, I mean, throughout the lectures, I mean, if you think of an ontology, it is in general is a graph, okay? But WordNet was initially built as a tree. In fact, if there are, I don't know, if, there are around, I think, 15,000 noun nodes, you will find only for maybe for I found only for one noun. I found more than one hyphen. Okay?
It means there is only noun to noun, that kind of relationship. So you consider this in terms of a tree.
Yeah, essentially you will I mean, so I mean, if you think of a tree which has 10,000 nodes, and if you have, say this is the tulip nodes and they are connected, okay, then you have only one cycle in this entire tree. Okay, so I mean, this looks like a very sparse graph kind of a thing. Okay, but that is the point. I mean, so if you consider it as a tree, then there will be only one path between any two nodes. But because there might be some loops, it says about shortest path. That is the point. Yeah, but if it is
generalized
directed,
graph,
yeah.
means we should consider generalized. In generalized sense, we should consider graph.
Yeah. So like, say for example, this is the hypernym relation, okay? And if you want to find out the relation, you want to find out the distance between this and this, so you will only follow this path, because it might have another edge like this, but it does not have it does not have any other path that links to this. Okay.
Okay.
Yeah.
And one more question is your PPT number 43, where you have mentioned that there are seeds and machine learning and classifier. So my question is that initially that is 43, somewhere in 43 where it is this one, machine learning, seeds and diagram is there.
I skipped, I mean, I had some hidden slides, but which slide you are exactly talking about?
Next to this.
Next
This
to
one.
this.
Yes,
Yeah,
this one.
Yeah.
Classifier. We shows the classifier. Classifier. This one. Yes.
Okay.
This one.
This one, yeah.
Yes. Seeds are there, and one more node you added here with classifier. Yeah. So is it the same concept of feedback?
It is not really feedback, but yeah, I mean, in some systems you have the idea of feedback, like in information retrieval systems, you get the relevant pages, and then user rates some of the pages, and then the search machine is refined. It is kind of that concept, but it's essentially, I mean, you are getting more and more training data leveled in this way. Yeah.
Okay.
So,
So
yeah,
here initially we consider small training data. So for
Yeah.
example, you consider any problem, suppose identifying a particular post tag, for example. So what can
Yeah.
be the size of training data? Small means what in terms of 100
Small
or
means,
1000?
okay, so if you want to build a machine learning classifier for your mother tongue,
Say post tag, for example.
POS tagger, for example. So, for example, you can start with as low as 1,000 sentences. Okay, and then in
Okay.
every iteration, you can get 1,000 more data labeled, or maybe
Okay.
5,000. I mean, if you are building a POS tagger, you should have at least in the size of tens of thousands, so 10,000 or 20,000. This is looks like a reasonable training data. Okay.
Yeah.
But,
Yeah.
1,000 training data, it can only be considered as a seed training data.
Yeah. Sit training data. Now, one more question I have, that is mention part, that is reference in case of NLP. It should be called mention entity mention.
Yeah, entity mention,
Yeah.
yes.
So if I have to identify entity mention,
Mhm.
then this 1,000 data, labeling the 1,000 data is sufficient in a specific domain.
Yeah, okay, no, 1,000 data is not really good data for named entity recognition. But in case of named entity recognition, what you can do is you can start with a small amount of training data, but then additionally, you could maintain a list of gadgetiers. Okay, so you do not really need to have all the data labeled in your training data. You can maintain additional gadgetiers in which you have a list of proper names like person names or something like that, place names, organizations. And whenever they appear in your text, you assume that they are like proper names. I mean, they have been they are mentions, but that may not be always the case. Say, for example, in English, Black can be the name of a person. Mr. Black said something like this. Mr. Green said. Even Green is a surname in English. Okay, so.
Yeah. Okay, thank you.
Good evening, sir.
Yes.
Sir, I have a question that I have recently started working in a regional language, and as we know, like most of the Indian regional languages are quite resourceless. So we have been working on it. It's a Pahari language, and now I just want a suggestion, like what can be the best models that can we use?
For what task? Can you? I mean, what task did you start?
So for building a robust POS tagger.
Okay.
Because of this ambiguation only, we are applying the other rule-based functions also on it, and it's quite improving the accuracy. But
Yes.
still, if you can suggest, so it would be a help.
Yeah, so there are some like practical things to be considered with the classifiers. Like if you have very little training data, the thing you should try to do, you should try to get this more training data using bootstrapping approach. If you have significant amount of training data, then the classifiers do not really matter. Okay, then most of the classifiers will perform almost in the same range. I mean, the naive Bayes or the decision tree might give you lower scores than SVM or neural nets, but they will be almost, their accuracies will almost be commensurate. But if you have very little training data, the most practical thing to be done is to employ the naive Bayes. Naive Bayes performs best with the lowest amount of training data, because all those sophisticated machine learning classifiers like CRF, Maxent, okay, they typically expect a large amount of training data. And particularly if your data is not very sparse, then also naive Bayes is also very good. So you'll also, I mean, you will also have to do this. I mean, so ultimately you will have to get more and more training data, and then you will have to try your hands with all the different machine learning classifiers, and then whichever gives you a better result. But you will have to essentially come up with more and more training data. Well, the one thing we did for some of our experiments, we designed some games. Okay, we entice the users to essentially level the training data. They did not know that they are essentially doing the annotation, but they took in a fun way. Okay, so you'll have to design some kind of games that this is a language game or something like this, so that the user unknowingly do some annotation. Okay, you can also take this approach for getting more and more training data.
Sure, sir.
Yes.
Sir, is any function in Python to create a term context matrix for the corpus? So our own corpus.
You can do that yourself. I don't know. I mean, I have not I have not done this with codes, but you can just, I mean, it is very easy to find this just for every word. I mean, you'll have to do it for every word in your data set. Okay. For every word, you will look into the context. Maybe you can take a shorter context like plus minus 2 words or 4 words. And then for every word, so you will have to take one word at a time. And say, for example, you find the mention of a particular word in 2000 sentences. So you extract them out, and then just you separate out the words that appear in the context. Okay, you place them in a file, and then simply you count the words, number of times in every individual word appears in its context, and that will give you the entire row for that particular word. And you do this for all the words, and you will get the entire matrix, term context matrix.
Excuse me, sir.
Yeah.
Some background noise are created. Prachita's Pathak. Who is Prachita's Pathak? Please mute your mic.
Yes, sir. Continuation
Hello.
to the yes. In continuation to the previous question, that what context you are saying? Say you mean you are saying that window concept, that taking the window of particular size. Yeah.
Yes. Like I said, when we are considering these context words, we only consider the context words that appear in the context window. So these are the context window. I mean, in fact, you will say that this is not a valid sentence. So I have only shown the words that appear in this 20 words context window, plus minus 10 words in this particular case. Okay. So you can take a different context like plus minus 5 words. So that will basically mean that the target word, 5 words to the left and 5 words to the right. You will only consider the words that appears in this window. Yeah.
Basically going towards embedding concept.
Yeah. I mean, embedding concept is basically this concept, and then it is an advanced concept. So because I mean, if you think of this, I'm getting some feedback. If you can mute your mic. So because this matrix will be very, very large. Okay. Because think of a very large corpus. It has 1 million words, unique words. Okay. So then in this matrix will be 1 million rows and 1 million columns. So 10 to the power 12 number of cells. Okay. 10 to the power 12 is 100 GB, I think. I mean, 1000 GB. Okay. And if even if you store short integers, I mean, even short integers take 1 byte of space. Then just to load these matrix into your computer, you need 1000 GB or 1 TB of RAM, which is infeasible. Okay.
Yeah.
So in word embedding, it uses this advanced concept of SVD, or the diagonalization of this matrix. Okay. But that comes from here only.
Sparse matrix problem.
Yeah.
And RT is just similar to this RT, that it's recognizing textual entailment, which you have mentioned at some point. So are there very specific algorithms for RT that one can be like, this is also RT related to RT, that if I am finding co-occurrence or this technique which you have just shown?
Yes.
Okay. So are there any specific algorithms mentioned that can be used directly for RT?
I mean, there is no standard library available for, I mean, because RT is a task, application. It is not like a NLP task. Okay. So RT, you will have to build your RT based using some other, I mean, you can use semantic similarity for using RT. But typically RT is a application. So if you are, I mean, so the task of RT, Mr. Singh, do I have some minutes? I mean, I don't know whether I'm exceeding my time because my talk was Dr. Singh.
Excuse me, sir.
Yeah.
Sir, one more questions from my side. Myself, SK Dubey.
Okay.
Sir, actually,
we will manage your time.
Okay. Yeah.
Sir, actually, I am currently working over the problem of similarities.
Yeah.
So, can you acknowledge us to any recursive functional theory which covers symmetricity and anti-symmetricity word similarities simultaneously?
Repeat your question, please. This is quite a complicated question.
any recursive functional theory in scope of primitive recursive functions, or any idea which covers symmetricity and anti-symmetricity simultaneously?
Okay, I think if I have understood your question, so you want to find out whether two words are similar but they're antonyms, right?
Can
Is that the question?
any idea, excuse me, sir, basically the theory of primitive recursive functions can be can we cover through the concept of similarities?
Yeah.
So can you acknowledge us how to explore
I
it
don't know really
further?
much about the thing that you are exactly talking about, primitive recursive theory or something like that. But if you are, I mean,
Especially
yeah.
Especially, sir, recently previous studies have been work over the normal functions, and I hope no any functions belongs to the recursive areas, recursive functional areas. So symmetricity and anti-symmetry both simultaneously can be covered through recursive functions.
Okay, I don't have a good answer to this question, but I could not show this particular slide. So I said that, I mean, how we could consider I mean, that two words are similar, like just like boy and girl, or just like up and down. They're very similar, but they're antonyms.
Yes.
Okay. So, I mean,
Yes,
boy and
yes,
girl are antonyms, but I mean, if you think of like good and bad, it will give you a very high similarity, but then they are different concepts altogether in the different directions. Okay. So, I mean, if you just think of this, I mean, we discussed that these are like PPMI, we are considering the PPMI values, only the positive values. Okay. So finally, we take the, I think we have this. Finally, so this is the PPMI vector of word 1, and this is the PPMI vector of the second word. And finally, if you consider the cosine similarity, you are doing the dot product, and then you are dividing by the length, because otherwise, if you have two different length vectors, their similarity will be less. Okay, but if you then length normalize all the vectors, then I mean, this is a concept that is used in.
Excuse me, sir. Can I request you to send your mail ID, and I will definitely send my problems with detail. So later on we can discuss over.
Yeah, maybe I will just give you this example. So the length. Why do we length normalize? Say, for example, we are interested in find the similarity with this particular vector. One is this vector P. The other one is this vector C. Okay. Now you know that cosine similarity essentially measures the angle between the two vectors. Okay. Now, if you take simply like what this is called, the length between the tip of the vectors, what it is called, I forgot the name, like the coordinates. What coordinates it is called? Not Cartesian.
Norm.
Is it the norm, or like what distance do you say this distance between the tip of the two vectors?
Relative distance.
Okay, I mean, I will take that as relative distance. Okay, so now if you find that the similarity by the relative distance, then you know that according to this, B is more similar than C. But then if you length normalize all the vector to the unit length, then all the vectors become a point on the unit sphere. Okay, and then if you compute the similarity between them, then you know that this vector C, the length normalized vector C, is closer to A than B. Okay, so that is why we typically do this length normalization. Okay, but finally, the point is, I mean, cosine similarity, you know that the cosine similarity ranges from +1 to -1. But because we considered PPMI, you will always get a score between 0 and 1. And in fact, I mean, most of the semantic similarity methods, they return you a score between 0 and 1. But if you do not take PPMI and instead just take PMI, then you will get some negative values as well. Okay, so that might, I mean, and if you can, I'm not sure, but you can study those values, and you may find that there you might find some antonyms which has very high similarity. Say for example, you get a score of -0.7. So you can say that these two words are very similar, but they may be in the opposite directions. good and bad and boy and girl and student and teacher, this kind of thing. Maybe student and teacher will be close to each other, but fast and slow, these kind of words, they could be in the opposite directions. And that can give you the indication that they can be antonyms. But I'm not sure about your question. So because I do not know, you may be very you seem to be very deep into functional theory and those kind of things. So I don't have a proper answer for that. And if you want to have any more questions, you can get back to me and drop me a mail.
Actually, this PPT is, I want to refer for that calculation part. So will you please?
Yeah, I can share the
calculation part. At least that
calculation.
calculation part is, and mathematical part is added.
The PPMI calculation.
Yeah.
Okay. Yeah, I will share you. I will send the slides to the organizer, Dr. Singh, and he can then share the slides with you if you want.
One more thing, sir.
Yeah.
One more thing. Don't mind me saying that initially, sir, we were lost because the voice was very low, and we could not gear up most of the concept. Though your lecture was very nice and the concept was very good, but we were very excited to learn most of it.
So
but
is
sir, we
it
lost.
that the voice was low or the internet connection was causing problems?
No, sir, voice was pretty low, because if you see in the chat window, most of us continuously was pinging that voice is low, but we were not able to interact with anyone because we don't have the phone number, we don't have anything.
Yeah. I'm sorry about this. I'm using I have a pretty good connection. I just checked the connection and it was like 80 MBs, both the upload speed and the download speed. So it must be some
One
problem
question,
with my
sir. One more
yeah.
question, sir.
Yes.
Sir, how did this similarity measure may help in sentimental analysis?
Not much really. Sentiment. I mean, you could use perhaps. I mean, say for example.
Yeah.
I mean,
because
maybe
it will give the almost the same similarities in the antonyms word. I think so, sir. So I don't think it will give more regarding the sentimental analysis.
Sorry, your voice is breaking. I could not get the question. Sorry, I could
sir,
not.
Just this thing I want to ask, that how do this similarity measure may help in sentimental analysis regarding in feature engineering?
Yeah, I mean, say for example, what you could do is you could come. I mean, if you were doing traditional machine learning, classical machine learning based.
So emotional, sentimental analysis. Okay, I'm just finding out the emotions in the tweets. Okay,
Yeah,
so
I
how
got your
can
point.
I?
Yeah, my point is, if you are doing it not using deep learning, that is,
Yes.
if you are doing it using traditional machine learning based feature engineering, then what you could do is, because in traditional machine learning, the most important thing is to come up with a very good feature set. Okay, so the better the feature set, the better your classifier is. So what you can do is you can come up with a list of words that appear most frequently in positive sentiment and negative sentiment, and then that list might not be very exhaustive, but then it is very easy to get a very big corpus, large corpus, any raw corpus, not any sentiment analysis, sentiment level corpus. And then you can find the similarity of the words that appear most frequently in the positive sentiment. Say, for example, great, funny, please, love, this kind of words like, okay? And you can find out the words that are very similar to these words. Okay, in that way you can populate your list. Perhaps. I'm not sure, but I have never done, I've never used sentence, I mean, or semantic similarity in sentiment analysis. But
okay, thank you all participants, and thank you to sir. Bhaskar sir.
Thank you very much.
An excellent presentation and a lot of involvement from the participants. So that speaks of itself that students, the participants are really taking interest and doing, and a lot of discussions, questions. So, and thank you for your time that you gave them to resolve their queries and had a discussion with them along with this nice presentation. So thank you, sir.
Thank you very much, Dr. Singh. Thank you. Bye.
Thank you.
Bye, everyone.
And so participants, we can take a 10-minute break. I think 15-minute break. Let's start with at 6:30 now, because it's already 6:15, more than 6:15. So we'll start at 6:30. Next session will start at 6:30. Okay. Thank you.
Okay.
I don't know.
Bhaskar sir, please send the PPTs. Lot of student participants are asking for that. Good evening, everyone.
Powering on. Connected.
चाय पिला सकते हैं.
Okay, so this is already 6:30.
So we can start now. A lot of participants are here. So
Yes, sir.
we are allowing all participants to unmute and have a discussion while we are going through this demo session. They are allowed now. So exactly as the topic, what we have planned today is how to use machine learning techniques with text data. Obviously, today, whatever we are going to discuss is a very naive approach. Don't think that in this FDP, I'm going to do any research, but obviously we will give you some techniques. Now, you think of certain applications like, I think 5-6 years back, we developed an application. We wrote a paper that is very highly cited. That was about the helpfulness. I think all of you might have seen, let me just, share the screen first. Screen 2. Okay. Is it visible to everyone?
Yes.
Yes.
Yes, sir. Yes.
So let me just open a site and give you a very practical example. What we did. Okay, so consider any product. So let us consider this one only, this headphone. And if you go to this headphone, go to this review section. Say this one. This reviews. You can see top reviews from India. Okay. And if you look into this review has just given 1 star. Obviously, this is a negative review. Looking at the star, I have not gone through the review, but looking at the star itself, I can say that, or anyone can say that this is basically a negative review. Okay. And this review was posted on 17th October 2021. Then you have another review, which is really a positive, very positive one. Very positive one. And that was posted on 15th October 2021. Then you 16th October 2021, then 14th October 2021, then 29. So you can see most of the reviews which are being posted here are in the month of, might be this product has appeared in October, November. But we have seen that for several reviews, if you look into the popular products, they have reviews in the range of almost thousands. While doing that research, we found that we have more than, sometimes it is more than 5, 6, 10,000 reviews for one particular product. So obviously, if you as a human being, if you are going to say buy that product, and if you are just going to read that review, 1,000 reviews or 2,000 reviews, no one is going to read. We also surveyed a lot, and we found that it has been surveyed and it has been found that it's really the top 10 to 15 at most. Otherwise, less people normally read less than 10 reviews to make a purchase decision. Now the question is, which 10 reviews should appear at the top? I hope I am able to make the problem clear to you. Is it? Can anyone confirm me?
Yes, sir.
So that was our problem. Which reviews, and this is not only in case of Amazon that we are doing this review. You will encounter several such sites where this sort of reviews, or you might have seen like Stack Exchange. I think almost all of you might be using Stack Exchange. And in Stack Exchange, you ask a question and then a lot of people gives their answer. And here again, with some popular questions, you will find that there are more than 1,000 answers. But if you are searching for an answer, you are not going to read all those 1,000 answers. you will be interested in having a ranking in those answers. And this ranking is immaterial whether it's a positive or negative one. You do not really require, you want an honest review, honest answer, whether it's positive or negative. Because even if it's a negative, like in this case, it's a negative review, and if it is at the top, basically you will go through this and you will make a purchase decision. Okay, this probably this product is not good. So there is no sentiment. I'm not talking about the sentiment, right? Now, if the sentiment is not involved, we are not talking about positive, negative. We are talking about as a whole, how helpful this review is to a user. So in that case, in fact, Amazon in 2007 probably introduced this idea, helpfulness votes. So if like in this case, I can click on this helpful, then this vote will be increased. As soon as I click it, this will be 96. Next time if you open it, it will be nice. Probably take some time nowadays. So I will request all the participants, those who have a problem with say Canvas link, because I have to do that. So please wait. There is someone who is continuously sending the message. So please wait. Let this, I was sitting for last 2 hours and doing all those updates. So please wait. After this lecture, I will surely do that. Okay, so I can click, and now I cannot click because I have voted, I cannot click. So initially when Amazon introduced this one, this was written like this: 95 out of say 1,000 people are now out of 120 people found this really helpful. Now they have changed the scheme. And you won't believe, then when Amazon introduced it in 2007, they had a profit of almost $75 million, probably, if I remember correctly. So there was a huge boost in the Amazon sales, and the profit was increased like anything else. So that means this helpfulness vote was quite good. Then what they started doing is they started ranking these reviews based on those helpfulness. So higher the reviews which have got most votes, that used to be on the top. So here you will see 95, then 26, then 20, 19, 8, 7, 7, 4. Still you can see. Here it is from other country. So for India, you can see the reviews are ranked based on the helpfulness vote. But my question is, there is a theory that the richer gets richer and the poorer gets poorer. I am not remembering the name of that person, but there is a theory. What it says here, that if a review is really good, or say initially it was good, but it has appeared for a long time, it is on top, so people will see this and again vote for this. But if you think that you have purchased that product and really found it that this product is not working well for you, or there is a major flaw, and you have written a big, quite healthy review, but that review will be appended at the end by this scheme. Because this is a new one, it will have 0 helpfulness vote, it will be appended at the end of that list. And hardly anyone is going to see that. So it will remain at the bottom only. I hope the problem is clear to everyone. And that's a very genuine problem in many scenarios, if it is on this sort of votes. Because whosoever has got some votes, they will always appear at the top, and they will be getting more votes and regaining their positions. Those who are poorer or those who are new, they are added at the end. They are no longer getting those votes. No, they are not getting views. So for this, in fact, we developed a proposal, and what we did. So when we decided to do that, the question was exactly from this review, what features we will extract? What are the features we can extract? And then obviously we surveyed, and we found that people have talked about the length of the total review. What is the total length, total word count in that review? Then what is the number of, say, unique characters in the review? So whether people have used any unique character. That means how many they have repeated, only the same thing they have repeated to make it a longer one. And then how many say adjectives have been used, how many single letter words have been used, how many 2 letters word have been used, what is the entropy of this review, and so on. So we decided about around 23 to 24 features. And then I think I must have those features appearing in that. Go to Scholar link, and from there I can find out. So that's the work we are talking about. So the features, if you see in this one, this paper is a unformatted version. So we have this. We have like polarity of the sentence, subjectivity of the sentence, how many nouns are appearing in that, how many adjectives are appearing in that, how many verbs are appearing, what is the place reading is. Now, how many of you know about the readability indexes? So there is a readability index, and readability indexes are basically used to check how good or what is the grade of English you have used in your text, which can be understood by what grade of native English speaker. So there are several measures of readability index. You might find it now in even this Grammarly have now introduced it. So there are many readability indexes like Flesch readability index, Dale-Child readability index. And then we also found out how many difficult words are there, because in Dale-Child there is a difficult words list of 30 difficult words. So what are the difficult words they have used? What is the length? What is the set length, stop count, wrong word, 1 letter word, 2 letter word, 3 letter word, long letter words, lex diversity, entropy, and rating. And based on this, we propose certain machine learning model. Because for any machine learning model, as the sir also told, you need to have a good feature. So that's what we will do today, how to extract features. And then slowly we will move on. Next day I will have, I think my team will have a discussion on the word embedding, and then this whole word can be given as input. But today we are only going to discuss about the features which we can extract manually from this text. Some of you may argue that these features doesn't have any meaning. Yes, I agree with you. But this is how machine learning works. Sometimes we cannot have a very strong motivation that this feature will work, but we have seen that most of the time it works. So we go with that. So with this, we are going to build today, and I will be assisted by my PhD scholars, Mrs. Gunjan Kumar and Ms. Sangeeta Singh. So over to you, Gunjan. You can share your screen.
Okay, sir. Good evening, everyone.
You can start sharing your screen first. And I think this code as well as the data set is already uploaded into Canvas. You can download it here. Otherwise, Gunjan, can you just paste this link of your drive into the chat window so that those who are unable to access Canvas, they can even get it from your Google account also.
Okay.
You can share this link. The link what you have sent it, no, but that link will not work. Okay, but from my side, I cannot do that. Go to that page. Share this one, no, NLP, FDP, that link and data set, how the participants will do, from where they will get the data. Although I have already uploaded this in Canvas, so you can download, those who have access to Canvas, they can easily download it. So share this one, the whole directory you can share. We go to this one, previous, back, yes. Now right click on this.
So, excuse me, sir.
Yes.
Sir, I'm accessing Canvas, but then I don't see any content after Monday.
No, just now in the evening I have, let me share this one and then I will see
Okay.
that. I have already, just now I have completed everything on Canvas.
Okay, sir. Okay.
So, Gunjan, please click on this, share with National Institute of Technology. Come down, come down. Not there, come down. Downside, share with National Institute of Technology Patna. Click on this. Here, anyone in this group will can link. Come, no, not done. Come here. Anyone in this group with this link and view, click on that. Click on that. Anyone with the link, lower one.
Gunjan, copy the link and paste in the chat window. Copy link.
Now let the link be created, ma'am. Please wait. Now you copy this link and paste it. Otherwise, no one will get access because it is restricted. It will be restricted to NIT Patna only. Now you paste it in the Webex chat window. Stop sharing if you are unable to find. Take your mouse to the upper part of the screen. Upper part. Hit the screen. अरे स्क्रीन के ऊपर तक ले जाओ और ऊपर जाओ. अरे और ऊपर जाओ. Gunjan, go up. Okay, so now it is shared. So you can access this one. Anyone can access, hopefully. So to participant, I will request they just check it once.
I think you all get the dataset link, and so I start the coding. For that, first we have to mount the Google Drive collab. So for this, you have to write the code. Dot collab. Import your drive. So you can run this cell with the help of Shift plus Enter, and then it run the present cell and create a new one. So while drive is going to mount, Everyone, please do the same on your system. Yeah, so Google Drive is mounted. And you can see that the drive option come here. So you can copy the path from here. You right click on that folder where is your data set is you have stored, and then copy the path and then write CD and paste that path. And when that's it, then you reach to that data set. Now we have to read the data set using the pandas. So I write import pandas. My file type, my data set file type is CSV. So I read in CSV format and write the name of the file. So it is a fake and real.csv. If you want to see the data frame, then you can type and run that. So you can see that you can see that there is a 3-column ID, tweet, and labels. Tweet is the text comment, and the label is on the basis of that text we have your label is given like real, or this comment is real or fake.
Madam, can you show again the path from where you have taken that drive this data?
Yeah. Okay.
Please.
You can see a small box in the left side of your window. So click on that. Then go to the drive. And where is and in which folder you have stored your data set, you click on that folder. Like my data set is in NLP FDP Day-5. So, and then right click on that, then copy path, and then you paste. After typing the CD, then you paste there and then run the cell.
Just to add to this, anyone, so first you can, on this screen, no, you can directly, instead of writing the first line or second line, what Gunjan explained, you can directly go to this screen. Let me just show you that I do not know.
I can show that one also.
So explain that. That is easier process, Gunjan.
Okay, sir. So you come to the data set where you stored, and then right click on that, you copy the path option, and you can store paste there where I'm typing.
I was not talking about that, Gunjan. I was talking about, say, let me just share my screen for a moment.
Okay, sir.
So I hope my screen is visible. So this is what Gunjan was trying to explain. Now from Google that collab, so this line she had written. Instead of this writing this line, once you have a collab notebook, you directly come to this one, this file. This icon, you come, files, click on that, and there you will get something like this. It's already mounted. If it would have not been mounted, say I'm not, I'm just dismounting it first. Mount it again. So if it would have been unmounted, I have just created it. Then you can click on this and this line will be automatically written. Okay, you just run that. And then next you come to your data. So like drive, my drive, and everyone in all different cases, it will be different. So it's not that always this path will be, so you cannot copy this path because this is going to be unique for your own machine. So you can go to this path, collab notebook where I have kept it, and then fake and real. And then here with 3 dots, I can copy this path and I can again paste it. Okay. So that will be an easier way, and there will be nothing, so there will be less chance of making a mistake, at least in the path. You can directly copy this path of file, or you can just copy this path, any way you can go with. Okay, so now continue.
So after reading the data set, if you want to see the first 5 row of the data set, then you can also write this. It will display the initial first samples of data, and if you pass any numerical value in the head function, then it will display the data amount of samples on your screen. So after that, and you don't know about the how many rows and columns in your data, so you can find out using the shape function. Shape. It will give you the shape of your data set. Now we have actually we want to work on the text of that data sample. So first I have to store the tweets on the text and label to the label. So my label is stored in the label, and the tweets comments are stored in the text. Now you can see that now our text become the tweets comments, and the label. So we can see that the our label is real and fake. It is it is a string type. It is not the numeric value, but our machine can understand the numeric. So we have to convert this label into the numerical form. Import the NumPy NumPy is NP, and label the indexed. What we have to label? We have to label the label of the data set data. So then apply. First list dot index. NP dot as array. The index. Um, Sorry, it is a indentation error. So I have to now see the label. So we can see that the actually you can see here is the first. Wait a second. Yeah. Yeah, zero index value is real, and the first one is real, then second one is fake. So you can see that in the arrays also the real is 0 0, and then fake is when it become fake, and then it become 1 also. So we can see that it is corresponding to the data label only, and it is correct. Now we have to find out some features from the text data set, as Sir has already told you. So we have to extract the features from the text. And now first one is I'm going to count the number of words in a sentence of that data set. So I write it a code for this data. So we are going to count the number of words in the sentence. Sentence, I mean to say that in a data sample. String str that text. And we are counting the word on the basis of the split as Bhaskar sir has explained this about yesterday. So we are counting the words where we get the space between the two words. Word count. So we can see that we get the word count of the every sentences in the data sample, and it is also a feature of the text data. Now my next feature is we can also count the character in a sentence. How many characters are in the sentence? So for this, you know that when function is count the length of any character. So and it also include the space as a character. I think everyone is doing the same code in your collab notebook also. So you can see that it count the character of that particular sentences. Okay. Now my next features, we have to think like this. Okay, we count the character and we count the word. Now what is the next feature? So we also think that the average word length of the sentences is maybe a features of that text. So for that, I am writing the code. So actually, Bhaskar sir has explained in the yesterday class that we can also define the function. So I'm also, here I am defining a function for finding the word for average word length. So it is
Okay.
Perimeter. Print the length of the word so we don't get any confusion. Now, for the average, we have to sum the character in the line. So we are in sum. Calculate average into sum of CJ. And then if we return.
Excuse me, ma'am. I have a question over here.
Yes.
For these labels where these are reals and fakes, so instead of these two labels, if I am having more than two, how are we gonna label them? Like for real and fake, we are having 0 and 1. So suppose it's more than 2, then how we are gonna label them?
Actually, if you are having more than one, then you have to, you can mention how many labels you have in your data set. You have to put there in that way. Then it automatically, index that label. How many different labels? So they index at 0, 1, 2, 3, 4, as much as you mention here. Sorry. Hello.
So
I don't
that,
understand.
that way, if any next label comes, then it will be numbered as 2, 3, 4, 5, whatever the count is, right?
Yeah.
Okay. Thank you.
So you get the average of that data. We are trying this on the tree, and so apply. So you can see that this was at that number of words. So, and after that, I have to calculate the average as I have already created a function. Every time I am writing the head, so because we can see and understand easily, you may not write that one also. So we get the average of that was that sentences in the word. Now after that, in the last day, you may know how to remove the stop words from the text. I think sir has explained. So now I am going to doing the same thing. I think you remember that for this, I have to import the NLTK. So NLTK dot download. Stop word. Now, NLTK dot code import stop word. Stop. Dot word. And stop word I have to store as a features of my data set. So data. And I'm applying the same function split. Down. Copy. if X in stop word stop. So data again. So we can see that the number of 6 stop words in the first sentence of my data set, and as in the many more. Now, after that, I have to find out the special character in my data set in every column. So for this, we have this tag. Reads, because I'm finding this in my reads, which is the text of my data set. So if that acts with hash, right? That hash, that is a hashtag. So this is count the total number of hashtags in my sentences, and now same I have to find out the numerics in my data set, as because while I am counting the features, extracting the features, so we no need to have the numerics in my data. So I am cleaning it. Here I have to is digit, and for the hashtag I am using start with hash. So here I am using the is digit. and this will give me the number of numerics in my sentence, numeric value in my sentences. Now there are so many features we have extracted from the text, and we store it as a okay. We can also count the number of uppercase in my data. So
can you explain these two lines in the stopword extraction? I didn't understand. Just go back.
okay. Yeah.
So importing the NLTK first, and then NLTK.download stopwords, you said. And what is the difference between that line and the next line, that NLTK corpus.import stopwords? So your actual stopwords are getting downloaded from NLTK.corpus import stopwords, right? And the above line and the second line, can you just tell me the difference? I didn't understand.
You want to know the difference between the NLTK download or
and this from NLTK.corpus import stopwords.
Ma'am, actually in NLTK, there is a corpus already built of stopwords for so many languages. So there is a corpus and we can download it. It can be initially, say, if you are working on your system, then you can pre-hand download it. So there is a feature that.
That's
These
why I understand. Yes.
These two lines are basically downloading that corpus. So once the corpus is in your machine, the next thing we are importing that corpus and we are using it for English only. So once we supply English, then this will give me the stopword for the English language. Now, if you want to see the stopword, so if you print this variable stop, you can see the stopwords which are occurring in English. Stop is, sorry, this line I have
So definitely the second line has to be written. Can't be write directly from NLTK.corpus import stopword?
Yes, if you are working on your system and you have already downloaded it, you do not need to download it again and again.
Okay.
So like on your local system, if you import NLTK, no. So if you install NLTK for the first time, that gives you an option that do you want to, like, if I give, say, something like this, let me just show you. Sorry, Gunjan, just
Yes,
write
sir.
in separate cell, just write NLTK dot download and double brackets only, opening bracket, closing bracket, without any argument. Create a new code and write that import NLTK. And then NLTK dot download, next line. Bracket opening, bracket closing.
Yes, sir.
So as you can see, this once we supply this NLTK dot download, a lot of options are coming. You want to download, you want to list, so you supply L here, you give L. And enter.
Yes, sir.
So you can see, browse down. You can see these are already available in NLTK, but not there on this machine. But these can be downloaded on local system if needed. Okay. So the ma'am's question was why we are doing this? Because we are importing those stopwords into our, we are downloading all those stopwords into our system so that the lookup will become faster. I hope now things are clear.
Okay, sir. Thank you.
So there are, you can see there are so many data sets, like there is a book on LTP grammar, so that you can download the complete book. And this list is quite exhaustive, quite a big list. Like Brown corpus, all of those who are working in NLP, they might have heard this one, brown corpus. So this whole corpus, this whole sentence is, the whole brown corpus is written there. So if you are working with brown corpus, you do not need to again create your own data set. You can directly download it from NLTK and you can continue. So these are the data sets, different data sets, different corpus which are available, and you can download it at any time. So normally Google Colab has not downloaded everything. So that's why when we are writing it on Colab, we have to download it. If it is on a local machine or on a server, we are using it for our own purpose, then normally while installing NLTK, we do all this. We download the complete list. And then we forget, we do not write these two sentences. So then we start only from nltk.corpus import stopwords, stop equals to English words. Okay. So that's the idea.
Okay.
Similarly, yesterday someone asked me, like, punctuations are not working. So whenever you try to tokenize something, the punctuation symbols are not working. Similarly, there is a corpus, there is a list of punctuation symbols like comma, full stop, colon, semicolon, and so on. So you can download it again. So you can supply nltk.download and then you can supply punctuation. So only that small corpus will be downloaded. I hope I'm clear. Okay, so Gunjan, go ahead.
Okay,
sir. I have one question.
Yes, please go ahead.
Voice is breaking. Okay.
Someone was asking a question?
Yes, sir, I think, but voice is not clear.
Your voice is not coming. Okay, there was a question. I think you have already answered that. How the labeling will be done if we are having more than 2 features. So we can replace, like we can write a replace statement that you replace this, say some x by 1, y by 2, z by 3, u by 4, and so on. Okay, to make it numeric one. Later on, in the later half of the course, we'll see that even these numerics 1, 2, 3, 4, this what is called as one-hot encoding. So there we will write in, if we have 4 levels, we'll write 4 columns for them. And then we write those columns which are present, 1 for that, and rest will be 0. So these are different ways we represent our labels. Screen size thoda bada kar lo, Gunjan. You make a zoom.
So what is the purpose of lambda?
Lambda, okay. Lambda is a way of writing small functions, inline functions, you know, in C++. So these are very similar. If we have to write a small function, just one line code, which will repeatedly work. So for that, we use lambda.
Okay, sir.
So it's like lambda x, and then we are passing the argument. So like here, lambda x, like we write no a function yx equals to something. Gunjan, just go to that, stay here. Like lambda x. So you are writing lambda and then x, and then that is equal to what? For every x in x split, if x dot is upper, if it's an upper capital letter, then you count that. You found the length of that. How many upper say capital letters are there? So that's what it will be stored in this tweet. So like in this sentence, you can see sentence number 0, CDC. So there, this is a capital. So there the count is 1. In the second sentence, there is no capital letters words, whole capital. So it's 0. So 0. And then here again, we have COVID. So, and then probably some other parts were also there in this one. So that's why the count is 9. This sentence might have 3, 9, and so on. So it's counting those things. Similarly, go upper side, thoda upar jao, Gunjan. So like here we had stopwords. So similarly, we were counting how many stopwords are there. Like in this case, the stopword is the. So cell number 19. So 0, like the is a stopword. In is a stopword. So you can, in fact, here, Gunjan, after cell number 19, no, or before cell number 19, you can just print that stopword. So you print that command stop, that variable stop, and that will show you the stopwords. Just write stop. There is nothing to write into print only. Okay. Okay, just run this. So these are the stopwords.
Right.
So if there is any occurrences of these words which are there in this list of stop, and C had calculated the stop, go up. थोड़ा ऊपर जाओ गुंजन. So here, so just stop word. So this is the variable stop we were talking about. Like we had a discussion on that also, that we are downloading the stop word corpus, whole corpus, and then we are just filtering out all those stop words which are there in for English language. And those stop words are stored in this variable stop, and that's what she had shown down. दिखाओ उसको एक बार फिर से. So these are the stop words. And now what we are doing, we are counting in the given sentence how many stop words have occurred, because several different people have different way of writing and different number of stop words they use. So counting that can be one feature. We are not sure that that will be really a feature, but counting that can be treated as a feature. So that's why we are counting how many stop words are there, and these are the counts. So similarly, in the next one, we are finding out how many hashtags are there. So we are counting everything which starts with a hash symbol. So here you can see like hash India fights Corona. So there hash COVID, and obviously in the rest part, we also have some more hashes, 2 hashes. So that count is 4. For others, there is no hash symbols in these 2, so it's 0 and so on. And now we can store, we are storing this. So what she is doing here is like data, tweet, hashtag. So she is storing everything. In data, we are storing like tweet, and then we will store it in CSV file, and then we will explain it again, exactly what we have created.
Sir.
Yes.
For getting that corpus, all corpus you have shown, that is L, where to use that L?
No, there is normally in a system, if you do it in your system, that will give you a option. A means all. Download all. So you give the first option. First option was D. If you remember, the first option was D, and if you press D, it will again ask for that L. So if you give D, it will again ask for you which package. So X, it will give list, cancel, and in local system, it also gives A, all packages. So if you press A, it will download all packages which are there in that corpus. So and in local machine, it also gives a very nice interface. There you can manually select also. A window basically will open.
Okay. Basically, different options are all. And
all, then you can list, and normally a window opens. Small window opens, and left hand side you have the packages, and then you can select them, and then you can press that you want to install all this, download all this. Those will be downloaded.
Okay, sir. Thank you.
Normally, as a starter, we also download all. We give A. It takes around 1 hour to download everything, and then we become free from all this downloading later on. But that facility is not obviously available for Colab. Okay, so Gunjan, go ahead.
Okay, so I have
just in uppercase, ma'am, right? So your code just now, whatever you have executed, it's just finding how many such uppercase words are there, right?
Yes, yes.
It's not the character, it's complete the words because you have
The
used
complete
split.
word. Complete words
Complete word has to be in capital.
in capital.
For in the upper, yeah.
Go just one cell above. Gunjan, just one cell above.
So just go.
So here it starts with has. Sorry, not that uppercase one. So here is upper. So is upper means everything is upper. If we just want to find out everything which starts with the upper one, then there is another feature function for that. I think starts with upper, something like that. Okay. So it's the complete word. Okay.
Can I continue?
Yes, yes, continue.
Yes, so we extracted the so many features and now we are creating
In
a,
fact, just a minute, Gunjan. I am sharing you a link, which is a book on NLTK, and you can get everything, whatever we are discussing. This book contains almost everything and all the codes, and this is free, so anyone can download it. So it's natural language processing with Python, analyzing text with natural language toolkit by Stephen Bird, Ivan Klein, and Edward Loper. So this book is free, you can download it.
so I am creating a combining all the features which we are extracted from that text in a single data frame. So I'm doing this. Average word. Stop word. Hashtag. And next one is upper. So you can see that it is our text and it is the word count, character count, average word, stop word, hashtags, number of hashtags in that sentences, and numeric value and upper has. And so we extracted the features and actually we are doing, here we are writing the head. You can also do and see the lower you can also use the tail. Tail and find out that it will display the last 5 samples of your data, and you can see that also. So you can see that. So we store all these as a features. So features. You see that this is like this, and it is extracting the features of the whole data set. Okay, actually, our system is understanding the numeric value, and so it cannot so we calculated that. But for this, if we are talking about the features, I think I have written the feeds in the features also. Okay, but it will not. I'm not including this because I have already extracted all the features from the that feed, so we no need to again include this. So now my features will be this, and we convert this features into the in the form of array. So I have to import the numpy. I think already I have imported the numpy, but still you can, and if you have already imported, then no need. So np dot as array is a function of the numpy, and we pass the features. Sorry. So we are seeing this.
Gunjan, I have one question. Here you are creating feature array with this as array function.
Yes.
And in NLP or in NLP, actually we create this feature array matrix with the help of TF IDF also.
Yeah,
So
we
what's
can.
the difference now in between these two?
Actually, here we are. We have already extracted the different features from the text, and then we are converting it into the array. But in the TF-IDF, we are having the different concepts. In this, we are counting the number of different words in the
Gunjan,
whole document.
Gunjan, let me just explain actually. Ma'am, as I have told at the start of this demonstration that we are not going to read this text as such. We are not really finding out any meaningful information. That means we are not comprehending the text, right? We are
Understood,
just trying to we are trying to get some features like say we are looking at a particular object, and we are just outside from that object. We are noting down the properties. So you can say some sort of static analysis sort of things. TF-IDF, on the other hand, is dynamic. We will try to comprehend the text, exactly what is inside that text, what is the meaning of that text. So we are not yet coming into that meaning part, okay?
Okay.
So that's the major difference.
Okay.
At all, we are not interested in whether what is written inside. We are just interested in how it looks. How many characters have been used, how many difficult words have been used, what is the length of average text, average sentences, and so and so.
Okay.
Without comprehending any meaning, without thinking of any meaning from that text. Okay. Whenever we'll think of the meaning, we have to go whatever you have suggested, like TF-IDF and then embedding vectors and so on. Then we can get the meaning of those texts. Okay. So that's why we are today we are not going into meaning. Next day, obviously, we'll go into the meaning and we'll talk about the TF-IDF, how to create vocabulary and everything else. Okay.
Okay. Thank you, sir.
Okay, now we get the features from the text, and we also get the
So there is a question, Gunjan, just a minute. There is a question, what is this feature? So as I told at the start that there are several applications where you just need to find out some outside how it looks. Like if you are say thinking of there is a challenge by PAN. Let me Can you share that website, Gunjan? PAN website? PAN, there is a website, and then you can check they conduct, say every year they conduct challenges. They have a challenge called a style change detection, or who is the author of this particular piece of text. Now, who is the author of this particular text? We are not interested in basically the meaning of those texts. We are mostly interested in the styles. Now, what is that style? So we can say that whatever we are calculating can be attributed, can be told. I'm not saying that this is style, but that style that can be treated as a style. Like while I'm writing, how many stop words I'm using. While I'm writing, what is the tense of those sentences? How many different types of tags I'm using? How many different types of unique words I'm using? How difficult words are using? I'm using. How many single letter words I'm using? And all those things. Now, how to find which features are important? So you can, there are several ways we can find out the important features in Keras and machine learning models. So now that becomes a question of machine learning, not the text analytic as such. Whenever we are human, we are treating, or we are basically thinking from the text analytics. We are just trying to find out as many features as we can extract. And then with the machine learning algorithms like random forest and everything, they can rank the features. These are the features on which I have segregated them, or I have classified them. So there are feature ranking algorithms available in different machine learning and even deep learning models. So Keras, there is a feature engineering or feature importance section, different separate section.
So can you tell me in your paper, which you have just shown on this helpfulness, how you have determined the usefulness and the ranking of these features?
Okay, there we use the feature that random forest and gradient boosting we have used. So those algorithms have inbuilt feature that they can rank the features. So those algorithms have those capability that they can rank the features, like this feature was important, this feature was slightly less important, and so on. They can rank all features starting from 1 to the last number. And then we have written, okay, these many features were found to be very important.
Okay, sir. Thank you.
So this is one say challenge. Those who are participating here, I will encourage them to take part in this sort of participations or say online challenges. In fact, these papers, whatever you will do the challenge, you will get a score, and then you can write a free conference paper called as CLEF. That's a conference held every year. I think in September, or normally that conference occurs. So you can see a lot of data sets available. Those who were talking about data sets, no? So some sort of data sets are available here also. I do not know how much useful it can be, but like author identification. So like from a tweet, you want to identify, or from a given text, you want to identify who is the real author of this text. So there are some work. You can say that these works doesn't mean anything, sir, but like plagiarism detection here. What is the originality of this text, and so on. There are a number of, and every year they release new data sets. So you can keep an eye on this. You can note down this website, those who are interested. In fact, you can paste it also, Gunjan.
And sir, I have one more question, because we are reaching to 8 p.m. Because I have gone through the whole notebook which have been supplied to us, this IPython notebook. So in the last, we have analyzed many machine learning models. 5 to 6 machine learning models have been tested for their accuracy. So my question is that, because means applying the machine learning algorithms and just reporting who is performing better is sometimes do not sound as justified task. So the question is, what is the final inference that we have taken after application of these 6 machine learning algorithms?
See, obviously this is not a research, but it means the whole work what I am presenting is not a very good, I'm saying that's research work. And that paper was, in fact, you can see it's a business oriented paper, not a technical paper. So they do not have a very, as you pointed out, not a very high requirement of say technical terms. But technically, these papers in a technical journal will be really of very low ranking. They will not have any novelty as such, until and unless we can prove that this particular technique will be supported by some fact that this feature is why this feature is important. Not only that machine learning algorithm is saying that this is important. Why people are now moving into that. Next is there are some cases like with some algorithms perform better than others. So as a researcher, early age researcher, it is a temptation, and in fact, we also as a supervisor suggest at least you should have a hands-on with all the possible machine learning and deep learning models so that they will be ready, and later on, whenever you will require, you can really choose one of them. So it's really basically a preparation task than a reporting task. That's the motivation, and that's why we have also kept here. At least people will have some data sets, some code, which if they are building some other applications for their own work, they can utilize some portion of this code from this to their work.
It is explaining that how you can build a model basically.
Yes.
Which features are possible in that given corpus?
So whatever now
like
Gunjan have explained, these are very less features. So there are a number of features, and now feature engineering, in fact, is a very tedious task. So if you talk about, or if you go through the papers 10 years back, 10, 20 years back, people were very interested in feature engineering. They used to manually handcraft features, manually extract features, and then used to build some regression or classification model. But with introduction of deep learning, things have changed. Now, deep learning model, himself, the model itself identifies the good features. So there we eliminate all these things. We do not require any deep learning model is basically a feature engineer only. Whether you talk about CNN, whether you talk about LSTM. So if I think all of you, those who are attending here, have a good experience in that, and you might have noticed that first 4 layer, 5 layers, 6 layers might be a CNN, but last 1 layer or last 2 layers are simple multi-layer perceptron, a dense network, and that's the classifier. The other parts, those 4 CNNs, where really the feature extractor, what Gunjan is doing manually, probably those feature extractors were doing that same thing inherently, but they are not reporting exactly what they have extracted.
Yes, sir. But still,
that's the basic philosophy of machine learning and deep learning.
Yes, sir. But still, machine learning we are using. That means if we want to build, means even if deep learning is there, but nowadays still we are using for some applications to build our own models using machine learning, no?
Yes, machine learning. Say, if you go through the history of AI, when we started making AI, it was a rule-based system, so everything was explainable. We know if a result is coming, why that result is coming. When we came to machine learning, in fact, that explainability reduced, but still there was some explainability. But with deep learning, right now, we are having very little explainability. And that little explainability reduces or stops deep learning to be applied in a variety of applications. Like you cannot use it in legal cases. You cannot use it in medical cases. If you cannot explain, you cannot use it in legal or medical cases. So we have to come back to that machine learning or basic AI models which can explain.
Yes, thank you.
Your voice is breaking down. I'm not able to hear you.
Hello, am I audible, sir?
Yes, now it's
Sir, I'm just asking one question that is it good to go for machine learning models instead of deep learning models for summarizing the text that are related to the medical, or in simple words, biomedical text, the clinical text?
I do not have very good idea about summarization. In fact, one of my scholar had just started doing work. Better, I will suggest you to keep this question and ask Dr. Sriparna, because she had, as far as I know, she had done a lot of work. So she can be in a better position to explain you what sort
Okay.
of models they have used and why they have used.
Thank you very much.
Your voice is not coming. I'm sorry. I'm not able to hear you. Yes, let us finish this and then probably we can talk for some more minutes.
Okay.
So now we have our data set available, as Gunjan has already explained or told. Basically, say one more thing here, what Gunjan has just presented, these are the raw features. Now with this raw feature, although she is fitting this, but this is never a very good idea to fit to use this sort of raw feature for any machine learning work. Just go to that output, just go up, last output.
Okay.
So this feature just above this, yes, this one, just above that. No. Okay, so look here, what is the problem? Why I'm saying this, that these are one of the major problems people ignore, or basically they do not know sometimes. The reason here is, if you look into this feature, the word count is of having value 29, character count is 190, average word. So if you look into the average value of this word count, somewhere it will come around, say, 15 or 20, something like that, the mean value. The mean value of character count will be, say, around what I can see from this one, it will be around 70, 80, something like that. Mean value of this might be, say, 4 or 5. Mean value of this might be, say, 2 or 3. And similarly, so the mean value of each and every column is different. So if you try to fit any model, that model may give you a very good result sometime, but it cannot be generalized. Later on, whenever you put it into practice, you are always going to fail. The reason will be all those weights which will be tuned will be tuned for these bigger values or these values. So it's always better to normalize it. So all these features should be put into a value in the range of, say, 0 to 1, or you can define your own range. I will put it in, say, 10 to 20, but always it is advisable you put it in the range of 0 to 1, all the features. So scale it down, everything from here in the range of 0 to 1. So all this will look like something, a value between 0 and 1. And then you will have a uniform training. It's like you are teaching, say, if I'm a teacher, I'm teaching chapter 1 with this weightage, chapter 2 with this weightage, chapter 3 with this weightage. And at the end, I am asking questions. And later on, if the question is having equal weightage from everyone, obviously students are going to get a lesser mark. Right? So please normalize it. Chalo, Gunjan.
So now we get the features from the text and the labels. Now, while we have to implement the machine learning classifiers, first we have to split this data set into the train and the text. So we can perform the training on the some amount of data set, and then some are used for the testing. So here I'm using the sklearn to split that data set into the train and text. So from the sklearn models, we import the train text split, and then we are dividing this text into the train text, X train and X test, and the labels into the void train and void test. And now I am splitting the features array, which is the features from the text, and the label, this one, and splitting at the size of the test set. We are defining how many have data are used for the test and how many are used for the training. So I'm using 50%. And actually, while we are splitting, if we will not define the random state. Then every time if we run the code, we will get the different results of the training and the testing, because the splitting will be done by randomly. So we have to decide it will divide the data set randomly, but having the state at 42. So it every time it will give the same result while we are running the classifier. So after splitting, we have to find out what is the shape of my training data.
Sir, here is a question. Since I'm a beginner, could you please explain me the significance of this x underscore train or the test variable? What exactly we are trying to achieve it over here?
Actually, we are dividing the data set into the training and the testing two levels. If you have some samples of data for the testing your machine, then they need to split it. But we have only the one data set, so I'm going to split it into the training and testing, where X train is we dividing the training for the text data into the two parts. X train is for the training, our machine learning classifier, and X test is used for testing. The same as for the label data. Actually, in the very first, like.
Gunjan,
Yes, sir.
just a minute. Let me share something and explain this one, because this is really very important one. Let me just share a screen, explain this. I hope my screen is visible to you. Is it visible?
Yes, sir.
Yes, sir. Yes, sir.
So that's the concept of testing and training and test. So you have collected data, say you collected data, because these tweets were also collected in a timeline normally. Wherever you collect data, usually it's whenever we collect a data, we make a schedule, and then say in one locality we collected data on one day, second locality we collected data in second day. Similarly in tweets, first day, second day, third day. But every day there might be say a new burning topic, and the topic of tweets will change. No, that's true. Yes or no?
Yes, sir. Yes, sir.
So whenever we are creating data sets, the data sets will be in proper order. Like say first 10 data sets might be referring to similar event, because that particular day one particular event was in popular. Second day might be something else was there, and that data set will be regarding that. Right. So data sets will be ordered. Now we want to divide this data set into two parts, training part and testing part. Why training and testing? Just like our exam. So we teach the students, and then at the end of the semester, we take an exam. And then only we can confirm that whether students have been trained properly or not, they have studied or not. So if we divide this data set, say first, say 75 data out of 100 data, say in this case, if I take, there are 19 data sets, 20 data sets. So if I say that first 15 data I will take for training and rest 15 for the testing, say for example, I decided, then what will be the problem? That because the first 10 data were from one particular event. Say it was the case that first 15 data was from day 1 and next 5 data was only from day 2. So you are training a model on a data set of day 1, and then you are testing it on a data set of day 2. Am I clear? Means whether I was able to give the motivation.
Yes, sir.
In any scenario, in fact, one of the major historical machine learning failure is US Navy made a system to identify intruders, basically image processing based system. In lab, they tested and everything was working almost 100%. When it was put into practice, it was giving 0% result. The reason was when the model was trained, it was trained in daytime. And when it was tested, in fact, that is required in night only, because daytime already there is everything. And then the model failed because the model has never seen any data from the night. So it could not diagnose, identify that. So that's why what we do, what that command, particular command, what Gunjan has written, what it does, if you look into now this X train. So we are in fact dividing this whole data set. This is my X, this is my Y. So now I'm creating 4 components. One is the training part of X and the training part of Y, and then testing part of X and then testing part of Y. So why that's why there were 4 different components. And if you look into this number, so the first data, the first index which was taken is 42, 48, 7, 14. So randomly some data is taken from this one, uniformly sampled from the whole space. And this has been never repeated in test. So in testing, we have a separate data. In training, we have a separate data, but that is chosen randomly so that the machine can see all possible days or all possible data set, types of data set while it is in training. I hope you are able to get this.
Excuse me, sir. Random state equal to 42. That means we can shuffle the data.
Yes. Now, since we are randomly selecting it, so random numbers always need a seed value, no? So that's the seed value. So how those random numbers will be generated?
So what is the significant? It is a 42 or we can change it here?
You can change it. The only thing is if you want that, if you are repeatedly running your system with different machine learning models, what someone just inquired that I have tested with 5 different machine learning models. And if you do it in 5 different days, and if you are not splitting on the same place, then since they will be getting different data, so they will be having different accuracy measures. So in that case, you want to ensure that every day my data is splitted at the same place. So that's why that seed value is kept same. But if you want that, okay, I want different random samples, like in k-fold sampling when we do, or basically if we want to average my output, then we take different cases with different times. In that case, we change the seed value. So once you change the seed value, you will have a different values, different rows coming into training and testing. But if you keep it fixed, same rows and columns will be coming. Means whatever was done first time, repeatedly it will be coming the same. But if you, as soon as you change the seed value, the things will change.
Okay, thank you, sir.
Okay.
Yes.
Excuse me, sir.
Yes.
Sir, is development test data is same as this test data?
Okay, sometimes people say if you have a separate testing set available, then this test is called as validation or development.
Okay.
But if you do not have a separate test set available, then we can again divide some portion of this testing as a validation. Okay. Sometimes we do it, sometimes we skip it. As the case may be, if you have plenty of data, you have liberty, you can do training, validation, testing. But if you have limited data, probably then we can get rid of that validation.
Sir, cross validation and validation are the same?
No.
Okay.
Validation is a same test set. Like we divide this training and testing. Say if you run this command 2 times. So there will be a training component, one validation component, and one testing component. And that runs for 1 time only.
Okay.
But in K, when we divide this whole data set, say into K number of components. Say if I divide this data set into 5 components. So every component will have 4 data. And with those, we say then out of this 5 component, with 4 component I will train, and the last one will be used for testing. Then I change it, that if I have used the 5th component for testing, next time I will take the first component for testing, rest 4 as training. Then I will move to the second component as testing, rest 4 as say training. And this way we compute for 5 cycles and we average the total output. That is k-fold cross validation.
Folding concept. Okay.
That is
Sir,
folding.
yeah. Sir, just a minute. What did you say about validation and test? I mean, there in some paper it is train and test only, and in some paper there is validation also.
That's what I told. So if you have,
Yeah.
so there can be 2 scenarios in the world. So
Yeah.
sometimes you have been given a test set separately and training set separately. Then in that case, what you do, you divide that training set into training and validation by the same command. Instead of calling it as test, there we call it as validation because we have a separate test. Like say what you say that pre-exam, that means sent up exam of class 11, class 12, and then the final exam of class 12.
Means
the final exam of class mock test, right? Mock test. That's
that
the
is
correct word.
validation data.
So that is validation.
Okay.
Okay.
So we
But
can
if
also
you are-
create like that. Means
Yes.
validation means if we have to separate train, test, and validation. So we have to run and then identify something as validation.
So from training itself, we take some portion aside and we call it as validation.
Okay.
Okay. So I think actually we use this concept of the validation test and test set to check whether our model is overfitting or underfitting. So it may be working very good when you test it with the validation sample, right? May not be working good with the test sample. So whether your model is underfit or overfit, if you want
It's
to know,
overfit.
we this
If
validation
that is the
test.
case, then obviously it's a overfitted model.
Yes, sir. In that case only.
If that is the case, then probably you can think of, say, creating some more data set or getting some more data set if that is feasible. If not feasible, then try to reduce the complexity of the models. So if it is a neural network, use some sort of dropouts or regularization in the loss function. If it is another machine learning models, there are regularizations. We call it as regularization normally. So we basically lower down the coefficients of some of the features. It's again that feature engineering will come into practice, but automatically the machine will decide, okay, these are the features which are not very important. So it lowers down their coefficient values so that their impact is less.
Sir, I have one question. Whenever we do testing, so we divide our data set into 2 parts, training and testing part. So is there any standard way, like how we are dividing our data into training and testing?
No. As such, no. It depends on the total data count you have. So say if we have only 100 data, in that case might be we cannot go beyond say 20 for testing. 80 data will be at least required for training. But if we have say 10 millions or 10,000 data, then probably we can go even 30% also, 35% also, 45% also. It depends on, because you need your target is to get sufficient data for the training, because if the model is trained well, it will be good for any testing data.
Okay, correct. Understood. Means same concept is applicable for machine learning and for deep learning.
Everywhere. Any data engineering task, we have the same idea.
Okay. Okay, sir.
Okay.
Thank you.
So thank you. Now let Gunjan finish her notebook, what she have prepared. Very quickly we will finish it. Gunjan?
Yes, sir.
So in fact, Gunjan, you can write one line, just 2 lines. Let me, from scalar, right? Just be above that, before applying machine learning models. Yes, there only, you write. From scalar, okay, you have not imported scalar. Okay, that will be done. From scalar, learn, L-E-A-R-N, learn, L-E-A-R-N. Import pre-processing. and then give a variable name. Next line. That whole variable name, that whole data sets. So you give a name, any name. So normalized data you can write, or X normalized. Equals to pre-processing dot normalize, Normalize, normalize in bracket the variable you are trying to normalize. So what was the name of that variable? Where you have the data? Data, it was something data. No, that frame name was data. No.
Feature array and yeah, feature array only we have.
Comma, norm, space देके norm equals to in bracket L2 equals to L2, small L2 in bracket. Sorry, bracket, comma, in quote, a single quote. Run this. So there were some strings also. Oh, you had one data set which was go to that feature. You had features. So instead of data, you write features. Features. You write features because there were strings. Features array.
Yeah, that's
Feature.
that's what it's.
Run it. Now print this feature array.
Yes.
Why? It's not occurring.
So normalized data.
It's not. It's normalized data, not feature array. Sorry. Yes, thank you for pointing it out. It's normalized data. The variable is now normalized data. No, not this one. Gunjan, while printing. Yes, printing, because you have stored this normalized value into normalized data. No?
Sorry. Yeah.
So see now what I was pointing at that particular time. Now everything is in the range of that 0 and 1. And that will make the job of that fitting quite simpler. Okay, now you can split this into train test split, normalized data. There the fitting will be better. So now you can skip this. We already had a lot of discussion on this train test. So we can directly, you can directly call the models, just a single model, okay? Because already we are at 8:30.
Okay, sir, only one request. Actually, I did not get that link for what it is for. You are going to use for quizzes.
Canvas.
Canvas. So will you please send?
So I do not know exactly how a lot of users are complaining, still complaining.
Because it will be required for quizzes. Now, at present, for any of the other work, we don't need it, but it might be needed at the time of quizzes.
Okay, I'm those who have requested, I have created, but still some people are requesting and they are saying that they are not getting it. That's a problem. In fact, what I can see, around 147 invitations have not been accepted till now. So it's very difficult scenario. I think if then we have to probably take some different ways. Tomorrow we have one quiz, no? Scheduled quiz.
Yeah.
Okay, let me find out. Anyway, you just send me a request again. Send me the mail.
Mail ID here in the chat box, sir.
In chat box also you can send right now.
Yeah. Okay.
Oh, so can I continue?
Continue.
Okay, now I'm going to apply the machine learning classifiers. So first we have to import it from for the
Okay,
accuracy
just
matrix.
just let me just go through this very fast. So say these two lines, the upper two lines, scale learned at matrix. This is required for matrix. Actually, there are three lines in any machine learning code. Those who have already experienced, they have written, they know that. For new, those who are just starting, for them, these are the three lines. Can you highlight this first three lines?
Yes.
The second cell. Three lines, first three lines of this one. So
Yeah.
these are the lines which really is related to machine learning. Next, yes, next one more line, four lines. So these four lines are really the code which is required for machine learning. What we are doing in first line, we are importing what type of classifier machine learning model we want to use, then creating an object in terms of, if you say it's an instance, and then we are fitting and predicting. So fit is basically the training. When we say fit a model, it's training. And when we say predict, that means it is giving exam. So it's testing. So while fitting, we give both the training and corresponding means the features as well as their labels. But while testing, we do not give exams, answer sets. We only give question and MCQ booklet. We never give the correct answer. So we only give the questions. That means the features are only given, and then the student will write the answers, and those answers will be stored in Y predicted. And then later on, we can check the answer given by the user, this Y predicted SVM, with the correct answer, which is already stored in Y test. So that matching will give the accuracy score. From there, we can get confusion matrix, F1 score if it is a classification problem, F1 score, and so on. Okay, so let us stop here today. We'll continue again. We are this whole week, and next week we are going to continue. And time to time, we will again discuss about all this sort of machine learning if needed. Okay. So
Sir, just one question.
Yes.
Sir, instead, like here we are having 0 and 1. If in case, like as I asked before, if it is more than 2, how exactly I'm gonna fed it to the models? Like,
it doesn't matter. Say in this model, it had 2 only. But if you see that those things are stored in a variable called as label, right? And this label can store any value, right. 0, 1, 2, 3, 4, 5, 6. It doesn't matter. Now, while we are going to train it, if there are more than 2, say in this Y train telemetry that is coming, some portion of that training portion of levels are coming into Y train. So currently this Y train have two levels only, 0 and 1. So it's just predicting those 2, or it is fitting for those 2. If it would have been more, say, number of such levels, then it will fit for them. You do not to do anything manually or anything extra for that.
Sir, in this case, we can use one.
Handles it.
Sir, in this case, we can also use one hot encoding technique.
Normally, we can use, obviously we can use, but for machine learning models, normally we do not prefer that. But obviously with neural network approaches and deep learning models, whenever even in machine learning, if you go for a neural network, then that time we normally go with, say, if here also, if we require 2 outputs, so there are 2 ways. You can give 1 neuron as output and output it as 0 or 1, or you can put 2 neurons as output. So both neurons will give a probability value. Like softmax function we have heard of. That softmax function, whenever we use, we give as many neurons, as many outputs are required. But if we give a sigmoid function sort of function, then we normally, that single neuron will be sufficient. So in case of softmax, what it does, it gives a probability for each output. Like say, if there are 4 options, then the probabilities for first one is say 0.01. For second, it is 0.3. For third, say it is 0.5. And for fourth, it is again something like 0.2 point something. Then you can find out the maximum of this. So you will, in this case, third one is maximum. So you will say that the prediction is 3, or the third output, or the third level is the correct. Okay, so that's how we go ahead in multiple levels. But here, this SBM, linear regression, and everything else, they can do it. Like logistic regression, SBM, normally they are traditionally 2-class classifiers. So they do it for one versus rest. So they take one class as a very popular class and then do it for the others, for rest. Okay, so they are designed in that fashion. So in those cases, normally people go for a neural network, but because that gives more flexibility. Okay, so can we close today?
Sir, I have one question. Sir,
Yes.
For my research work, I'm creating my own data set. So I just want to know how to validate the data set.
So labeling you are doing by yourself?
Yes, sir. Right now I'm only doing.
So you do not have any other choice. You have to write your own code and some data sets, and from that only you will validate it. But while taking those, while writing, my suggestion will be you go through some papers, the way we create, like how these labelings have been done. For that, there is a specific say guideline. Like we labeled it by at least 3%. This was labeled by at least 3% or 5%. And then there will be some confusion, and then those confusions will be reduced. And then there is a kappa measure for that. How what was the agreement between different labelers? Because labeling, if you write in a paper that I have labeled it by myself, one labeling, people will not take it very seriously.
Correct.
You have to label it by 2-3 persons, and then you have to give a kappa measure coefficient, we call it as, where you can say that, okay, out of this labeling, there were 90% or 80% cases where people agreed, all 3 people agreed on the same label, but there were another, say 5 to or 10-12% cases where people did not agree. I say spam, he said no, ham. So we thrown out all those say examples, and we finally stick with this data set.
Okay. So what term you have used? Kappa.
Kappa coefficient.
Gunjan ma'am, can you just show me that normalization lines of the code? Just scroll up.
Thank you, sir.
I'm getting some error here. Okay, I need to keep that in L2 in course. Okay, fine. Thank you.